Yay. Hmm, here we are. Hi, everyone. Huh, let me put up the chat. Okay. Ah, yeah, Sean, Shviraj, Surabhi. Good evening. Yes, good evening to everybody. Cool. Okay. Vaishnavi Vinod Khodwar. Good evening to you as well. Okay, cool. So this character that's a little bit baffled. What kind of expression is that? A little brooding, moping, a little scared, a little freaked out with you guys with your homework. That's you. It even has some Trojan colors and everything. Oh, yeah. Yeah, exactly. Let's put off the exam as long as we can. You know, you guys are lucky with your exam. It actually, the way the timing worked out, it's not like right away. But then for my other courses, the exams are actually next week. Wow. So you are relatively a little bit shielded, but it means you have a little more to study as well. For example, all of today's lectures absolutely included. Okay, we'll talk about exams another time, okay? I'll definitely give you a midterm sample for sure, so then you can know what kind of questions to expect. And don't worry, it's very straightforward. My exams are never hard. The exams absolutely need you to understand, what all this is about. So no memorization required. So there's absolutely no fill in the blanks, or something like that. It's really it focuses on what you actually know. It's called understanding, not regurgitation. We don't want the exact words that are in the slides. We want what are in between the words in the slides. Literally read between the lines. Okay, so I have very little to add to all of this. We still have all this. Is still true. You guys are doing your homework after all. The homework is very interesting from your pizza questions point of view. Okay, so I suppose the practice it will. We can hope. Okay, but I'm not ever going to guarantee that. I'll just say that you cannot hold me to it and say, "Wow, the exam looked nothing like a sample." I'm just being honest because a sample cannot be a template. Okay, I couldn't just make an exam and just change all the words. So I hope it's reasonable. I hope you're reasonable about it. But I'll purposely promise to not completely change it. That's like misleading. Okay, I would never do that. But overall, it would give you an idea of what questions to expect. That's for sure. Cool. Okay. And yeah, the Piazza questions are extremely interesting. I look at them. Unfortunately, no time to jump into replying all of them. But I have a great CP team, of course, so they take good care of you guys. Yeah, the questions reflect like all your thinking, how you actually approach the problem. It's neat to actually watch your minds in action. I enjoy it. And it's not a very straightforward homework. I told you this last Wednesday. If it is the most simplest SQL questions in the world, just 2 or 3 line SQL questions, you don't have a sense of challenge or mastery. You still doubt if you actually know real SQL. Whereas with this homework, at least it forces you to think. It says, "Wow, how am I going to do it?" Not difficult, but more like amusing frustration is a good way to put it, because you know that the data is right in front of you, the answer. It's somehow in all those tables. Like, how much money are we making, on the average per day? If given a calculator and then a small enough table, you can do it by hand. So the answers are not impossible to get, and they don't require hard differential equation solving or anything. But you will not have just a small table. You won't have a ballpoint pen. Somebody wants to click on it when you're sleeping at night on thousands of patients. So then the question is something you can do by hand, just visually, verbally looking at it, right? How would you write SQL for it? Yeah, that part is not trivial. In a way, it is nice that that part is not trivial because the world pays you for having that knowledge. So once you know all this, people actually, pay you for writing SQL. If it is so simple, then they wouldn't hire you. So think of it like that. Initially, I thought I had to put in a table. Yeah, exactly. So that's exactly right. You don't actually need like much more really. Just like the basics to answer the question. Ideally, many tables you had in your first homework, the design, you could just simply make real tables out of them. That's the most fun because you can then see your design come to work. But based on what the question is asking or based on your own design, sometimes that's not possible. In other words, your initial design was not sufficient. Then definitely feel free to add anything you want. Totally. Exactly. So that's funny. So exactly what I was saying, CG was also repeating or stepping. Yes, correct. So it all depends on how you design your homework one. In the real world, they're not two different things, meaning nobody would penalize you if you went back and changed your design. In the real world, all this happens, together, so to speak, meaning you make an ERD, the client approves it, and then you make a small toy database and like do a soft launch. People actually start using it. And then the owner comes and says, how much money did I make today? Can I find out? And then you think, wow, that query is either hard to write, slow, or maybe I should change the table or add a few tables so that your query is possible. So you go a little back and forth. Right. Yeah, so CGS kinds of, that's a pretty useful tip actually, because other questions almost follow a very similar pattern. So that's a very nice, you know, little tidbit that he provided. Cool. Okay, so all that is wonderful. Let's do this couple of lectures. These are very, very interesting today. We're going to talk about connectivity and performance tuning, and we'll have some discussion questions, and possibly go back and do a tiny bit of this because I asked you about this. I asked you to think about what this actually means. Okay, so I'll come back and ask you. I think we'll have enough time for that. We'll just take it easy and have fun today. Because the actual hardcore topic, believe it or not, ended last week, so I didn't tell you that. Okay, so in a classic relational database, you know, uh, theory course, I guess, like what is the nugget? What is the heart of the database? It's all of these. It is about modeling data. Eventually, you settle on a table like a relational model, and then you can draw diagrams to show that model. And this is what you did for your homework. And that this is all the same thing. There's many models, but relational model is the best model. So you have relational models, you have tables, which is basically rows and columns of data. And then you can extend that with a class hierarchy abstraction. And then you keep tables very clean. You don't have too many things going on in the same table. Just like programming, have many functions and then call each other. Don't put everything in one function. So all this makes a lot of sense. And then SQL came and made it all real. So this is the homework that you're living through. And you can say, wow, this language is so powerful, but I need to know how to use it. Then we talked about transaction management and distributed databases last time, and this is where the real world comes in. So how about the entire world, wants to buy this, airline ticket, and who's going to get it? That is all this idea of transaction management, and then distributed transaction management with the whole two-phase commit. Do we need to make? Okay, so you guys can like answer your own questions. Okay, I'll just keep an eye on it, unless that is related to this. I want answer. Okay, you definitely feel free to ask and answer. All right, so transaction management and distributed databases is really how the entire internet works. So anything from Grubhub to Lyft to buying an airline ticket to even signing up for courses, this is really how it works. Because again, courses can fill up if you're are too late. There's contention everywhere, so there has to be locking involved. And when multiple machines are involved, they all have to succeed or fail at the same time. So you need to have a two-phase solution. So the notion of two-phase solution shows up here and here, and in the real world that helps. Okay, so then that is really the end of all databases, believe it or not, as far as tables are concerned. You know really how to pretty much deploy tables on a small system. So now next what we can do is increase that a little bit more, meaning learn a little more about these two things. This one is specifically about how through the internet, how can you open an Amazon app or LinkedIn app or even an eBay app or any app and then interact with an actual database. How can you make a bid? Or how can you look up someone's resume or apply for a job? Those are all ways in which people actually interact with the so-called backend database. So the question with this whole connectivity is what is the connectivity between the internet, a web server, and a database? That is actually what this is about. So it is not more relational theory. There's no more nothing new things to tell you about primary keys and foreign keys and integration integrity violation. It's all things you already know. But then how can you actually interact with the database? So it's highly useful. If you pair this idea with web tech, then it becomes even more useful because web tech is all about the web server part of it, the client part of it, and the web server part of it. But this one picks up from the web server to the actual database. It's almost like hop. How does information hop from system to system? That's what this is. Focusing on the very last piece, which is the database part of it. And then this one is also fascinating because how can you make your queries run really, really fast? It doesn't matter how fast machines are. You can have 64 cores. You can have GPUs with 1024 cores. In the future, you can have DNA computing. You can have laser chips, optical computing. You can have anything you want. But then proportionately, what's going to happen is the world will also collect even more data. Right now, we think that some things shouldn't be collected just because there's just no place to store it all. But then when you have the speed, then when you have the disk storage space, then people will actually fill it up. And then this question always still remains, even 50 years from now, how can you make the queries be fast? Because 50 years from now, people still are not going to wait for a long, long time when something can be done about it. So then here the question is, what can you do about it? And this is actually a two-part answer. The one-part answer would be from the database point of view. So from the people that actually administer the cloud database, the data engineers, what can they do to keep the system running, as fast as possible? Likewise, the SQL programmer, the front-end programmer, or the business analyst, the person writing the SQL code, they can also do something at their end to make the queries run fast. So if you do both, then absolutely that's the best situation. And all the big internet-facing companies, Facebook, Google, and Amazon, Apple, Microsoft, all of them, that's what they do. So everybody has to do their part, and then it runs as efficiently as possible. Then we can have some questions about it. So like I said, it's all like very fascinating because it is real world. This is how things work. All right, so database connectivity. And once again, I'll just put up the bamboo thing, or maybe I'll do it here. Let's use this LC thing. Literally canvas. I've drawn it. Okay, so I'll pick like a very fine thing today. It's this. So here's our client, by which we mean a browser on a laptop, or maybe a tablet, an iPad, or definitely a phone. They're all clients. This is what you sit on your bed, and just like do things, interact with the world. And so then the world would actually be this web server, except connected to a billion other web servers. Make that 50 billion. We don't even know how many billions, right? Massive amounts of servers. So they can all like bring you stuff. They can bring you the whole world. But then among those things are also multiple of these databases. I'll just draw one just to keep it simple. There's a database here. And this is really where all your tables are kept. So all your rows and columns are all kept here, right there. And so then when somebody runs a SQL query, directly finally at some point the SQL query is going to come here, and the engine is going to run the query and then get the results right back to you. So you are sitting here and just browsing on your phone, just swipe right, swipe right, swipe left, swipe right. It's still the same thing. You're doing stuff here. And then somehow your requests are being sent to a web server, and that in turn would forward the database request onto a database server, and then the database server would answer back with a response, and the web server turns that into HTML and then sends it back to you. Or maybe it sends you raw data and you can format it yourself. So there's this extra piece here. Therefore, this is the connectivity. So when we say connectivity, we don't talk about this part. It's like, how is the web server actually connected to like an Oracle, LiveSQL, or any other kind of database, Postgres? How does that work? So the short answer would be, I'll just talk for a few minutes here, then we can look at the slides. The short answer would be that this database, which is ultimately a bunch of just processes that are running on with some disk space, will not be part of the same web server machine at all. That's quite dangerous for one thing, because if somebody then hacks and takes over the server, then they can completely have access to all the data. So it's a very scary prospect that can happen. So we wouldn't do it for that reason. The second reason is if this machine goes down, if it's all just a bunch of disks that share HTML pages and also database tables, then if the disk breaks and somebody did not make a backup, then not only will the web server go down, but you'll lose data as well. Or even if you get backups, it's going to take a while to bring it back. We shouldn't couple them. Or if they're using the same address space, once again, they run out of address space, or they're using the same RAM, then one is going to slow the other one down. For any number of reasons, this web server should not have the database engine also running on the same machine. That's a complete no-no, okay? But there's another very interesting possibility. The web server can directly talk to the database, meaning send SQL queries and get responses. Or there's something very interesting we can insert here. One more level. In CS, right, we have this cool joke, this meme that we have that says, any problem in computer science can be solved by introducing one more level of indirection. So you have indirect access to a database. So this is the level of indirection. Just add one more thing in the middle. And that is literally called middleware. So the middleware is also a machine. It's like a server. But then its job is not to serve HTML. That is the job of this. Middleware's job is also not to hold data. That's the database's job. So the middleware literally mediates between those. It can actually get database requests. It even can do a little bit of transaction management, actually, to make sure that multiple people are, cannot read and write the same data. It's pretty much like helping out the database system, okay? Yeah, definitely. Can we write some caching logic? Yeah, it actually does, So that's a very cool question that one student asked. Can this do some caching? Can it act like a proxy? Absolutely. That is one of the jobs of the middleware server. So I have some slides on middleware, then we'll definitely answer these questions. But yeah, for sure, the middleware can actually stop some of the queries from actually getting to the database itself. If it recognizes that it's the same query that happened just a short time ago, then you can assume that maybe the data didn't change, so I can then directly give you the response back. Yeah, so the middleware does like lots of neat things. But that is the only extra thing that is necessary. But if you don't need middleware, you can directly send requests to a database machine. Okay, so this is what we'll talk about today. Like, how does this part work? Okay, not this part, not this part. Huh. Active record, good. Okay, so clear and to our slides. Okay, chapter 14, very good. And yeah, so learning objectives, right? It's about, there are many ways to connect, first of all. So this is almost like a history of the internet. In fact, it's the history of PCs and maybe even a tiny history of Unix machines. So I'm going to give you a little bit of history of computing, okay? Because connectivity in the past does not look like connectivity we have today. Today we can do pretty much everything is service based. So that means, some machine, for example, Amazon might have a credit card validation service running, meaning if you then submit your card number, say you change your card number, it's not Amazon's job directly to find out if your card is valid or not. Visa or somebody else, even a separate business, can do that. So Amazon just makes a call. They'll send you a card number, and then it says valid, not valid. That is called a service. So in that sense, our connectivity is expanded like crazy. So anything that you do on your phone, we have no idea where all in the world it's actually running. It's highly connected. But in the past, it was not like that. The connectivity was very specific. And so I can give you a little history of what that is. And then this whole web database middleware, that is the thing that I do in the middle. I called it MW. So that can be used to integrate the database with the internet. By internet, we mean web servers. So this thing can sit in the middle. One more thing it can do is extra security and authentication. It's like a firewall almost, so that the hacker does not directly get to the database. Because the worst thing you want in the world is for your database to be just exposed to anybody. You definitely don't want that. So middleware is one more way to help with that. And then this is all this history of what we call CGI. In other words, this is almost as old as the web itself at 1993. In 93, when people realized the web server's job should not be just to serve HTML. I mean, that should be its main job. But then it should also be allowed to do a few other things, almost like a little private backdoor. Like, what if we can make the web server run extra software and maybe compute some data and send that back to the user? So that is not a static HTML page. There's no page at all. You can make up a page. Those are called extensions, okay? That's what these are. So there's a whole world of those. I'm going to talk about those. And then this web application server, this middleware is another name, is web application server. So we call it WAS, exact same as middleware. So what are all the things that middleware can do? I brought up some of those. Can the server compute unrelated to it? No, I don't think it does that. The middleware is not that sophisticated, unfortunately. The middleware usually only, has one backend database it communicates with. At that point, in fact, the web server can actually do that, okay? That's how you write your app. So at the back end, when you deploy an app, say using Flask or Express or any number of frameworks, then you, the back end programmer, can do that, where the server would actually send one request to one machine over here, a different machine, a different request, and then integrate all the data together. Absolutely. Yeah, for sure. Yes, then the answer is yes. So when you say middleware, do you mean ORM layers? Middleware can do ORM, but then that's not really even middleware. By middleware, I mean things like WebSphere or JBoss. That's what I mean by middleware. Cool. So I'll show you some of the slides, but middleware can do ORM, but that's not the middleware's job, okay? If you want, you can do that. It depends on what the database is organized as, for example, and what the web server wants. So I would not connect them, but then the middleware could do ORM. But if you wait just a little bit, then I can tell you exactly what the middleware would do. Cool. So then XML, so in this chapter in the book, they just randomly threw some XML in. So I don't think we'll even talk about XML. We can do all that in big data, like NoSQL data. Right. XML is just a way to not use tables anymore. So we'll just hold off on XML. We'll never talk about XML. Yeah, right. Not exclusively, you're right. For the most part, I definitely agree. But there's still a legacy of world, where XML is still used. Sure. So I'm going to say a combination of them, but increasingly JSON. And then cloud computing, again, I'm going to hold off on it. Just maybe say a few words if we have time. But then we have the entire second half of the course to talk about all of this. Yeah, this is basically the future, by the way. Maybe this is now. In other words, ultimately it's come to a point when all your backend apps are actually running on a cloud such as AWS, and they're running inside containers even. So you can have many versions of your app all running separately from each other. And then those containers, the services that are running in those containers, can talk to other containers. So basically, cloud pieces are talking to other cloud pieces, and then you get your results back. So this is absolutely like how it's all going, right? But then not yet. I think we should focus on this part because that is the first like 4 or 5 bullet points because that is what the whole connectivity stuff is all about. Okay. All right. So then connectivity. It's about database middleware. So no matter whether it's an actual middleware or not, it's more like a software middleware. It provides an interface between the web server. When we say application program, it really means the web server. Because again, if I go back here for a minute, any program that you're running, you're obviously running on a client. So everything starts with a phone or some iPad app. But then, needless to say, very quickly, unless the iPad like does all things by itself, it ends up at a web server. So when we say application, we actually mean the application that is running on the web server because it's going to give you that data. But now what we mean by middleware in that little slide there is it's some kind of service, it's some kind of API, it's some piece of this web server that is eventually at some point go and end up in a database, a DBMS, holding a DBMS, and then get results back and go back the opposite direction. So it can be an actual machine like middleware, or it can be just some extra small things that the web server is running. So that's what is in that slide. When we say in that slide right here, when we say middleware interface, it's what the thing that I just drew, this little thing that I drew. Okay. And then, so what do you mean by a database? We can actually expand the word database itself. So data repository or source, it actually says data source, okay? So what do you mean by this backend? Like this right here? On the one hand, it can actually have table data. You can have actual tables where there's static frozen numbers that are sitting there and served to you. Or in general, like I said, what these days can happen is a so-called service call can be made. Like there can be another web server here. And it's not, the server is not asking the server for direct data. The server can actually maybe compute data. Maybe it's a random number generator. Maybe it generates like a probability distribution. Or maybe this is hooked up to a telescope and it even takes a picture when you ask. So the data these days can be dynamically generated. Okay, it's dynamically generated data. It's no longer data that is just sitting on tables. So when you think of the word data, think of more expanded ways of getting data, like real-time measurement or real-time computation, some abstract data. We call all of these loosely data. So together, they're all called data sources. Therefore, the web server communicates with data sources. Yeah, right. Sure. Yes, exactly. So, when you talk about search and indexing, that's a whole world on all to itself. In fact, search data can also be called data. So maybe, like things like Solr, etc., Hibernate, they're all like running here. Okay. And so Elasticsearch, all of that can be over here. But the web server still communicates and gets data back. Sure. This is semi out of topic, but off topic, but not really. Still relevant. All right. From now on, the word data can actually mean dynamic data. Okay. That's it. Now comes the actual connectivity. History. Okay, history looks like this. I can just summarize it myself, and then I'm going to actually tell you a little bit about this. In fact, I'll tell you this part, and then we'll tell you about Microsoft. Microsoft is a world all unto itself. So we'll deal with them separately. But meanwhile, pick a different color. This is what happened before SQL came along. In fact, this was actually the reason for SQL. This is pre-SQL data connectivity. So when we say connectivity, why is in this lecture? Because it is a connectivity between maybe a PC, an old-fashioned PC, an actual monitor that looked like this. Now it's a big monitor, huge electron gun, everything. Old-fashioned monitor, a massive keyboard and this thing on the side. But somehow that is all communicating with some kind of database. So before SQL standardization, all that came along, here's what happened. Oracle was selling, the Oracle software at the time, but no SQL, it's pre-SQL. And then maybe Microsoft was also selling, the Microsoft, like SQL Server. That's over here, MS SQL. Okay. Different vendors. Then here's what had to happen. If your PC ran an application that specifically had to go to Oracle because you paid Oracle money and you have Oracle installed, and then you wanted some results back from your tables, like for your homework, you had to write custom code that directly interacted with those backend tables. There was some kind of C++ API for it. And so you had to write one program to make that happen. And then supposing the next year you migrate all your data to Microsoft because they give you a cheaper deal, and then now you don't have Oracle anymore. then amazingly, the program that you wrote last year will not run on this because Microsoft publishes their own API to access their relational databases. Even though conceptually they're all the exact same data, same rows, same columns, even same data type, the column types didn't change. But just the way Microsoft stores it, okay, in the binary format changed. And therefore, all the things that worked on Oracle failed on Microsoft. It was a crazy world that drove everybody just insane because all of a sudden, programmers are not highly productive because you're learning a brand new API again from scratch. And then anything that used to work beautifully, just days and days used to work, now you have a bug because you don't understand this API. All that used to happen. That is called native connectivity, okay? Okay, so SQL, I see, ODBC. Oh, that's interesting. Yeah, that's funny. So you're migrating data from Excel to Oracle. But that's a good thing to do, right? At least the data is not anymore in Excel. Wow. Okay. Yeah, not .NET. That's funny because Microsoft provides like native drivers for everybody. Yeah, so there's one way to bypass everything that I'm going to tell you. They're all more and more beautifully wrapped, object-oriented ways to get to the back end. But like this, you can ignore all of those and just directly interact with the back end yourself. More fast, more efficient, but also maybe more dangerous in a way. Sure. So I'm going to tell you all these layers. Microsoft invented many, many, many layers. But then the story is in order. The story was before SQL, there was no standard to access data, meaning there was no SQL. So imagine you had to do SQL querying, SQL-like querying, but without SQL. That is exactly what this is, okay? So it says native SQL, but not really native SQL. There was actually a world when there was no SQL at all. I'm actually starting before that. Then what happened was every vendor thankfully implemented the SQL standard. So SQL became a standard very fast because the world started using relational databases like crazy. So when SQL became a standard, thankfully, all those direct ways of getting to data still remain. Like it still remains like over here, .NET DB drivers. But now the world has also an additional SQL engine. So every good relational database vendor, whether it's Postgres or SQL Server, or anything, Access, Paradox, Foxbase, SQLite, any number of them, as long as they're relational, they will support SQL. Because in today's world, nobody would use something that has no SQL. Nobody's willing to learn some crazy API, which you might change anytime and just go out of business. Then they'll get stuck. So we need SQL today. So thankfully, every vendor today has SQL. And the SQL is pretty much the same on all machines, but there are small flavor differences. For example, one might say subtract, one might say minus when you do table A minus table B. But those are minor. We can easily just look at the manual and just Google it, and we can fix it. So let's move on. Okay, that is the SQL part of it. And then I'll come to Microsoft. There's a whole world here. But then very quickly, this also happened in like 1995 March, as a matter of fact. Sun amazingly put out the Java programming language. So you can go to sun.com. You could go to sun.com and then download this executable, and then you ran it on your machine. Then it installed the JVM, and then the Java compiler, and all kinds of things that give you a browser plugin. Then the world all of a sudden said, wow, we have this new language called Java. Before Java, there was pretty much only C++ to do serious things. But then Java is like C++, but minus the fangs, meaning all the sharp parts are removed, specifically no pointers, okay? And so it made programming like very simple. And then Sun realized even way back in the 90s that data is like so damn important. And so then they wrote this thing called JDBC. It's basically just Java classes. You actually import JDBC star. So Java database connectivity. That's what JDBC stands for. So Java database connectivity is basically a Java API. It's a pretty huge API. But then in the abstract, that's all it does. What it does is you write a Java program. I have examples coming up again. You write a Java program, just good old Java. Then in there's actually a database connection object. There's actually a connection object. And then you initialize the connection object with the actual username and password for the database that you already have. And then you get a connection. And from the connection, there's a statement object. Then you make a new statement S, and then you can put a SQL string into it. And then you can tell the statement object s.execute. Then what that does is send that SQL string all the way to your database. And then your database will run the SQL and get the results back as Java data types, meaning you can iterate through them using Java code and then look at what responses you got back from the table. So it all of a sudden made programming a lot of fun because you could use then Java data types, and then you can have a hash map, you can have what, you can do all kinds of cool things with Java that you couldn't do with Oracle, with SQL rather. So then you use both for its own strength, okay? So that is the notion of JDBC. Therefore, Sun came and shook up the world. Then every vendor then had to do the following. So then how would JDBC run on, for example, Oracle SQL? So Oracle had to support JDBC, meaning JDBC is almost like a front end, and then their own native drivers are the back end. In the past, you had to directly program the native driver, but now some JDBC program that you write, Java is supposed to be portable from day one, and so then the vendors had to guarantee, it doesn't care if you're Microsoft, that code that I wrote in Java, the dot class or the jar file, if I run it on this machine, it should run because the backend driver's job is to translate these statements into actual Microsoft stuff that Microsoft knows about. So Microsoft pays their driver engineers to write that driver code. Likewise, Oracle updates their driver, and then SQLite also writes like a JDBC driver. So the front end is really what the world uses. The back end of the driver is the native part. So from now on, we never have to worry about the back end. It's pretty cool. Wow, there's like all kinds of things here. Let me see. Okay, cool. Yeah. See, this is all getting recorded, so if people want to go look at it, I can go read it afterwards. Yeah, thank you for all these fun facts. Okay, so therefore, JDBC therefore was a nice add-on to SQL because now you can do SQL through Java. Okay, so that is what all of this is. But meanwhile, you have Microsoft, their own amazing country. Microsoft did this when they wanted programmers to give access to databases. This only for Microsoft databases. Microsoft made many databases over the years, by the way. So in addition to things like Microsoft SQL that they sell, they also have PC databases. One is called Access. Still, many small businesses actually run Access is a relational database. There's one more that they made called Paradox. Wow, I used to actually run Paradox queries. Oh my god, takes me back 90s, crazy mid 90s. So Microsoft made money by selling PC-oriented databases. You would not have a Mac version of Access. You would not have a Mac version of Paradox. This is basically running businesses running like PCs. Like the whole maybe 1,000 PCs in your small business all over the world. Then they would actually have Access and Paradox installed. And then how would then the programmer, the PC programmer, have access to the relational database? Microsoft provided their own API called ODBC, Open Database Connectivity. When Microsoft says the word open, yeah. So when Microsoft says the word open, they actually mean open as long as your name is Microsoft. They totally don't care about other, things like Mac or Linux or something. And so ODBC ultimately is just like a bunch of DLLs. Okay, that's really what it is. And so then if I actually go here really, really fast, if I go to C, program files, drivers or something, C, I think it's C Windows, right? Let's actually try it. So C Windows System 32 drivers, like all this. It's like you basically go in the depths of your machine, okay? So C Windows System 32, okay? And then like drivers. Somewhere you can actually find something like ODBC 32.dll, ODBC 64.dll. So ODBC is actually a driver that ships with the Windows operating system, okay? And we can just quickly look for it, but if not, just give up. If I delete it on the machine, then many things that might depend on that would just stop working. Not here, so I might probably look in like not even System 32, but just Windows, something else. If someone else knows where it is, just let me know, okay? B system, nope. Okay. It's somewhere. Maybe not important. Just look one more time. Or maybe Windows drivers or something. They hide things like all over the place, okay? But somewhere there's no DBC, maybe it's not important. But it's a DLL. So DLL is just simply how Windows ships, right? It's got like tons of things. I want to look one more time. So it just becomes one more DLL, that's all. As long as people leave the DLL alone, so Microsoft is obviously allowed to update it, then they will actually, oh, I see Windows System 32. Okay, that's where I am. Let me look. Thank you. Is it driver data? Probably not, right? I thought I looked at ODBC. Oh, I see. Although it's Microsoft drivers, you would think that it's going to be here. Sometimes it might be called MS something. Look for a minute. Oh, I hope not. In the past, I've actually done stuff like that. Okay, I would delete it just to show it, but I would always put it back. Okay. I don't know. We'll find it some other time, you guys. Okay. Probably find it over the break. But there it is, okay? So it's just simply that whole ODBC layer is just simply shipping to us as a DLL, that's all. But as long as I have that ODBC in the directory I tried to show you, I'm running Access to a Paradox. Then some front-end UI that I have, for example, I'm looking up recipe databases or my friends list or something, would be stored here and then accessed through ODBC, okay? So let's actually move on. These are very interesting. And then just to tell you more, I want to show you the picture. Therefore, that was the bottommost layer. So from any application, you could always reach all the way down and use ODBC and directly get to all the Microsoft data. Then, over the years, Microsoft tried to wrap this in bigger and bigger and bigger and bigger layers so that it becomes a little bit easier to program. I call it alphabet soup. It's almost like Chinese DAO. So DAO Jet, So Jet is like, I think it's called Joint Engine Technology. Very, very interesting, So they invented so many different ways. It's called remote data objects. And I have all this in the slides, by the way. So this is not the only time that you'll see it. It's all here. Just as a quick preview, then we can go a little faster. Yeah, so then they invented so many different, this one is called object linking and embedding. That's what it's called. So OLE. In other words, they have so many different technologies that are all Microsoft specific. OLE is Microsoft specific, and so is .NET. So AD is, I think, access data objects. So all of these different ways in which ODBC can be used a little bit more safely. So because of .NET, this API, this, by the way, the most recent API, ADA.NET, you can write code these days in things like Visual Basic, thank you, look for it. Visual Basic, or Python if you want, or C# for sure, or even Java. So all those languages eventually can call the services that are in this API. They're all service-based, by the way, internally Windows services. All of Windows is entirely service-based, okay? Okay, so then they'll come a long way compared to ODBC is my point. But that is all Microsoft's own evolution. It's putting up all kinds of things. Cool. So then let's then look at some other work. Right. So, yeah, Yuda. One of the first things that Microsoft did was they called all the collection of alphabet soup universal data access. Again, as long as the universe consists of Microsoft, they don't care about Macs and Linux machines, right? Or some other Unix machine, SGI, Sun Microsystems, to hell with that. If you're a PC, then it's universal. Then it's just a collection, simply a trade name almost. So what did UDA consist of? It consisted of ODBC, the bottommost layer that directly gives you access to Microsoft databases. OLEDB actually is interesting. So OLEDB is object linking and embedding. So I can spend a few minutes on it. What it is so Microsoft has this technology where, say you have PowerPoint. So make a PowerPoint slide. The slide has some kind of a chart that I'm trying to put up. But then here's Excel. And then Excel stored the data. In the thing that you want is actually in a little XLS file here. So what you can do through ODB is, and maybe you're editing Excel even. So then the chart that you want is over here. You can have a live connection between Excel and PowerPoint, and then pretty much grab that chart, which is an object, this whole UI, the view, and also the model, the data that's inside is an object. That object can literally be embedded so that it's almost like a live connection. So if you update this, this will also update. That is called object linking and embedding, OLE. It's called OLE. And Microsoft has had this for a long, long time. It's pretty useful. This way, apps can communicate with each other. You don't have to save one, export it like a PNG, and come and paste it. It's like a live connection. All right, so then OLEDB is simply an extension of OLE, where now this OLE can also go from PowerPoint or even Excel to an actual relational database, and then through the ODBC magic that they have, can actually come back and embed some object over here. In other words, you can have a live connection with databases. So that extension to OLE was called OLEDB. It still exists, okay? OLEDB. All right, so now OLE, ODBC, OLEDB. And then ADO.NET, which I'll tell you at the end. There's some slides. It's all, like I told you, the most modern incarnation of all of these. Meanwhile, all these older things continue to work. So Microsoft, never completely obsoletes anything. So if you wrote something 20 years ago, it still will compile, it still work. But then you have more layers, newer ways of getting to the same data. But that's what you need to know. So then back to native SQL. So I told you when SQL came along, this notion of native SQL. In fact, when we say native SQL, it's not even SQL. Imagine the word SQL gone. It's more like native connectivity. Oh, so she's putting all kinds of things. Okay, well, good. So if you don't want to use Microsoft, then you can use like some alternate implementation. Good, very nice. Okay, so then this is the truth. The truth is that this connectivity, native connectivity, was different for every machine. So it's just a pain. Okay? Then people standardize it. So now back in Microsoft's land, the things I told you, I can explain a little more. ODBC, first of all, is Microsoft's own drivers to all the PC databases, such as Access and Paradox. So call it call level interface, okay, just all that. It's widely supported, obviously, Microsoft supports it. So any program at all that runs on a PC that wants to store data on a PC Recipe database is the most obvious thing, right? So it's a PC recipe databases. The 90s, everybody had those. Just put all your recipes in one place. Then how are they going to store the recipe? That's exactly how they would actually put it in a Paradox database or FoxDB or something. And then this is the key. It allows the Windows application to access relational data. That's it. But then, the application is running some SQL. You're not running it. You're filling out some form in the UI, and then some SQL is written, and then magically data appears. Good. But things like ODBC still, like if you are the programmer writing this application, then they have to know ODBC. So people thought it was too low level. Wow, I'm looking at raw tables, can you do something a little bit better? Then Microsoft said, okay, we'll come up with all this DAO, RDO, all of that. So here's a diagram that's going to explain them. This is what DAO is. DAO stands for Data Access Objects. But now for the first time, it is actually object-oriented. Yeah, so then these databases are named before. Access, FoxPro, DBase. I'll also add Paradox. There's one called Paradox. All of those can now be accessed from any Visual Basic program. By Visual Basic program, I mean it can be a video game where you store your video game data. It can be how much money you're making, all your stock information can be stored. So it's mostly just the UI, but it means, there's some front-end application that is storing data in the back end. And then that's what DAO was. And then Jet was very interesting. So, he put up a whole bunch of things about Jet. Jet is basically like a data engine, meaning this piece of technology that Microsoft had that was also used as an API. Through the Jet Engine API, you could make a call to like all of these. So therefore, your application can go directly, this application can go either directly to ODBC or through DAO or through Jet to ODBC. So Jet was an intermediate layer, still exists. That's why DAO.Jet. And then also they made one more. In the meanwhile, just like DAO. All right, so these are getting more and more wrapped in object orientation. Remote data objects, so RDO. No, that's a little different. So RDO is now about remote database service. So by remote, we don't mean the internet necessarily, more like a LAN connection. So you have a LAN, and then now your PC is running some application. Maybe HR wants salary information about you. But the salary data is in some other part of the LAN. It's on a different PC. All the pieces are wired together with the LAN. So now your machine can actually, through the LAN connection, make a connection to a remote database, then get data back. That API is called RDO. So as long as you have the credentials, now you can run, your application can log on to a database to anywhere in the system. That is called RDO. Okay, so it is higher level, definitely it is object-oriented, it's all true. But in the end, again, I don't want to go back and look in the mission. All of these things, ODBC, DAO, RDO, practically any part of the alphabet soup, they all exist as simply DLLs. They're just Windows dynamically linked libraries. Why do you have so many DLLs, by the way? So what is the deal with all these DLLs? Does anybody know? Why does every driver, these are all kinds of drivers. Why do we need so many drivers? Why are there so many DLLs? Why not just one big, oh, I see. Thank you. So why not just one big, giant thing called Windows 10.exe or something? Right. So can you explain why that is? You're right. So what is the advantage? Still so desperately trying to look for it. Can you tell? Because it bugs me. Like, where the hell did that go? Dynamic linking, you're correct, but why? Still the question about why. So you don't have to load. Yeah, right. Okay, so in a way, that's correct. So in a way, all of this is together the correct answer, okay? Okay, if there's any little bug, okay, in some part of Windows, maybe my login screen doesn't work anymore. Exactly. So what Monzo, if everything was one giant executable, maybe a 2 gig Windows executable, every single bug would just entirely affect the whole system. So thankfully, because of DLLs, that's what the Windows updates are. So somebody fixes just one DLL basically, and then in the middle of the night, it just goes and copies it, and then the old DLL is gone, and then you have the new one. That is what the whole purpose of all that is, okay? So therefore, ODBC is also one of those. Maybe Microsoft can maybe do some optimization in how memory is used in the ODBC, and then they can just update that. So in the real world, all these APIs are all shipped as DLLs. By the way, this is really what the word API means, okay? These days we use the word API on the internet in a very, very different way. We use it like it's a query, and you can send some query parameters, and the query comes back with some kind of a response. That is not really what an API is, but sadly, too many people that did not know all this started using the word API for that, and it stuck. So when you call them something an API endpoint, it's actually not an API. This is an API. All these are APIs. All right. Yeah, right, exactly. That's interesting. Yeah, as long as you somehow keep them in like separate environments or something. Okay. Even TCP/IP, by the way, is all done as DLLs. There's all kinds of Windows DLLs. I used to look at all of them. Moving on though, ODBC. You're right. So then this notion of ODBC, how did Microsoft, provide this thing called ODBC? So ODBC again is in two parts, like with everything else. There's a higher level part that the Windows application programmer writes the calls for. That is the actual API that is exposed to them. There's also a lower part that communicates with the raw uh, database itself. So let's use Foxbase or something as an example. So then Foxbase comes with its own Foxbase drivers in C++ that know exactly how to get all this relational data that you want. So if you know that API, you can write some program that directly can get all this data. But if you use ODBC, ODBC is standard after all. Microsoft doesn't change it. You keep the whole runtime. Therefore, anybody like this application can make ODBC calls. Some other application can also make ODBC calls, and those calls can be swapped from one program to another, meaning it's the same kind of ODBC calls. Then the ODBC call would be translated by the driver itself to the lower level calls for Foxbase. Supposing you do the exact same thing for Paradox, same thing, you write ODBC calls, but then those calls would be translated to Paradox or Access's low-end API, and then translate back. So all the APIs exist in lower level and a higher level. And the idea is only the higher level is technically exposed. You're not supposed to rely on the lower level because the application, the people that make Paradox, are allowed to change it. It's almost like public versus private. So you shouldn't actually depend on it because someday it might fall away. All right, so those are all neat things. Therefore, ODBC definitely does exist as a public face for all these databases. All right, that's why this is okay. So higher level API walkthrough. And the driver manager, so the manager that's sitting exactly at the database is the one that's actually going to get all the client connections, translate that, then get data back to you. So ODBC communicates directly to database. Yeah, exactly. The driver is in two parts, but the driver is ultimately what is communicating with the database. Your application is not directly communicating with the database. Okay, so these are all just layers. So the picture that I promised is here, okay? So in the end, all the things that I drew and erased multiple times are all right here in this one thing. This says Word, Access, Excel. You can also include PowerPoint, you can include a video game, you can include what. Even emails, for example, might be stored on your machine, or your contact list, whatever, or is all here. You can always go straight to ODBC. That's what this straight path is, because Microsoft will always support ODBC. And so on a PC, this is always guaranteed to run. This runs on Windows 95, runs on Windows 98, Windows 2000, anything. This always runs, is always part of the PC. But what does it actually do? It is in two parts. The top part is what the programmer programs, but then they get translated to native calls, Oracle call, SQL call, ODBC. Okay, so this is actually the raw call to Oracle straight. You could do it like that. Or you could do it through a driver, so this one is a little bit different. But in the end, those calls are being translated to lower level calls. I think that's really all you need to know. But look at there's something on the right. MS Excel today, if you want, you can write some little Visual Basic add-on that can make a call to Jet Engine. The Jet Engine API is also available. And then that will then translate and go back to you. Or you can also make from Word, for instance, make a DAO call, and then DAO will also translate. Or you can make an audio call. They're all like layers depending on each other, okay? So in today's world, most of the time, there's something even bigger than that, which is the whole .NET, 8.0.NET. But when you have multiple levels of access available to you, you try to use the highest level because it's the most shrink wrapped, most object oriented, hopefully easier to use. But then if you don't mind the pain, you want efficiency, you want speed, then you will do the opposite. You directly write machine code, right? It's the same thing. You just directly use the ODBC API. Cool. So then that simple little picture says, wow, Microsoft over the years tried like so many different things. They keep on inventing newer and newer things. But then they stopped with the whole 8.0.NET. But before 8.0.NET, here's this little slide that explains a little about OLEDB that I already told you about. So OLE is when one application can get objects from another application through memory, just direct memory exchange. And then the database extension is OLEDB. So then this one is like, they call it a middleware, it's like an API. So this way, any program that wants access to data can go to OLEDB. And then when the database is updated, let's say the registrar, okay, they have some front end that is running. You keep an eye on all the students every term. Then as the scores come in for the students, the GPA are all getting updated. Then the registrar's view can also automatically change because it's polling once in a while to OLEDB. So it's a live connection, think of it like that. This is actually interesting. So this notion of COM, how the hell does OLEDB actually work, okay? So OLEDB works because of this idea called components. So these days we take components for granted. A component is simply a very beautifully encapsulated model view controller. You can call it a component. But then in the 80s, when all this came along, a component was a new idea. You know, it's a very cool idea. And definitely Microsoft did not invent components, okay? They're just using it. Components came from like, even bigger worlds, Unix worlds I'll tell you about. But then right now we'll just say, in fact, it's called OMG. OMG did not stand for, oh my God, it actually stood for Object Modeling Group. So Object Modeling Group were the ones that first started using these public components. So Microsoft has a version of that. In any case, a Microsoft component is actually very interesting. In one app, a component is really just simply like an interface. It's a common interface, literally. And so then say this application is running, they also have a common interface. That common interface is common to here and here. In other words, all the applications support this thing called component object model. What that all eventually translates to is this. When you want to do OLEDB, say this is your database, right? And then this is your actual application. What does it mean for the application to grab the data and actually put it like a chart? Like how does the actual object exchange work? It works through this layer called COM. So OLEDB would use COM. COM actually means that regardless of your application, it's like the same object format, the same members, same methods, the same actual slots for all the members, what is what is actually being exchanged through the wire. It's almost like they have one common object. It doesn't matter what PC application, they all use the same object, which is not true at all. In other words, internally the object is like God knows how it's represented in memory. Likewise, here it's represented entirely different way. But when you go through COM, this will do a translation and make it a common object that everybody understands. Go here. This does the opposite. Take that common object model and then translate that to whatever this application wants. So applications can magically exchange live objects through memory, okay? That is exactly what COM is. So COM is cool. And then they actually made a COM Plus. So these days Microsoft has COM Plus. You can easily Google all of these. It's all like part of history. To say, I'll even Google COM versus COM Plus, okay? Yeah. These are cool things. I've looked into those. I'm not going to say use them, I know exactly. There's also DCOM, I forgot. Yeah. So, they just make it better. That's all. Okay. So, like COM Plus is really COM Plus Plus. There's like so much big answers. Okay. But this is all a very good idea underneath. The idea underneath was it shouldn't matter what the application is. In fact, COM is actually so cool that it's even better than what I'm telling you. In other words, here COM services. Yeah. So all of this, for example, it looks like this. They're all like C++ APIs. Should I show you something? Okay, maybe the overview. Yeah, programming overview. Let's look at that. Just one page where you have some detail, okay? Okay, so all of this, the threading model that is used to exchange the objects. I mean, they're going into some pretty great level detail about what all of this is. I'm going to ignore it, okay? But then in reality, it comes down to the fact that these applications can be written in any programming language. Maybe this is a Java application running as a jar file. Maybe this was compiled and run through C++. Maybe this is some Visual Basic thing that's not even compiled. But they can all exchange data between each other because they're all using the same COM model. So the COM object translation is occurring everywhere. So even endians don't matter. So with the OMG, this whole COM actually works across like a LAN connection, even of Unix machines, or even across the internet. So what OMG, the bigger version of COM lets you do is you can have one Unix machine that has maybe got little endian in the microprocessor. And then here the microprocessor is big endian, so the whole bit order is different. And then the programming language, everything is different, application is different. But then somehow a program running on this machine with the little endian can exchange an object with this machine running big endian, a completely different programming language, and then take that object and do something to it and send an object back. That is super cool that they can do that, okay? So COM is just doing the same thing in the PC world. And OLEDB depends on it. So now you understand how databases, data can actually show up in applications. Part of the whole, there's no handshake in the sense of servers and clients, absolutely, because the interface is predetermined from both sides. But I think there's some kind of handshake for sure, initially to establish the connection to exchange objects. But otherwise, there's no strong handshake. Cool. Well, I see. That's interesting. Cool. Yeah, COM was a good idea, no doubt at all. All right, so then a series of COM objects. Ultimately, COM objects are what go back and forth between a database and some front end like PowerPoint. Okay, so you can just ignore all of this. This all just simply says consumers are your high-end application like your PowerPoint. and then your provider would be the low-end database that is, returning data back. So it's all the same idea, said many different ways, but it's cool though. All right, so this is what I started to tell you. COM was not Microsoft's idea. In the Unix world, it still exists. It's called OMG, Object Modeling Group. They had a thing called, this is the bigger version of COM, Common Object Request Broker Architecture. Request brokering. So this means how can two different applications send a common object across from each other. So it's called the CORBA model, okay? So CORBA is what COM is based on. That's it. Okay, so you can read more about this. Yeah. So then, Microsoft COM versus CORBA. CORBA is a superset, is what I'm going to tell you. So CORBA is cross-platform right there, okay? Because CORBA was written so that any Unix machine can communicate. Macs could participate. PCs could participate if they wanted. Microsoft said, to hell with CORBA, we'll make our own. That's why they made COM, actually. So CORBA is an industry standard. That's all pretty neat. And then go to Microsoft, both have. But they're not talking about Microsoft. The first thing they'll say about COM is it's Microsoft specific. Okay. Strengths of COM. Okay, all this. Yeah, Microsoft backs it. Well, what they should have said is it basically only runs on Microsoft. So it's Microsoft or else. Okay, that's what it is. And then they just give it away so people can get hooked to it. So done it. And then you can write COM stuff in any programming language. All right, cool. So COM versus CORBA. In the end, conceptually, they do exactly the same thing, which is to exchange objects across any two diverse applications that know nothing about each other. So that's the beauty, okay? The applications don't have to know anything about each other at all. One application simply makes a request here, give me this object, and then the other application formats it in COM format and sends it. And then the first object says, I made some change here, you can have it back. So two different programs are communicating. In Photoshop, you're painting something, and then in Maya 3D application, all of a sudden that becomes a texture map, and it shows up in a character's body and stuff like that. So it lets live programs, meaning two different programs running on the same machine or on a LAN, exchange objects across from each other, and now we can exchange database objects, meaning you can read from any database, on the LAN. That's what OLEDB is. So it's simply an extension of OLE. Okay, moving on. OLEDB, yeah, when OLEDB first came out, it was really just a C++ API. And so scripting languages, specifically Visual Basic, people could not use OLEDB from Visual Basic. That was like a big drawback because there are many Visual Basic programmers. They're not hardcore C++ programmers. So then Microsoft said, okay, we'll fix that. We'll wrap OLEDB in something called ADO. I mean, look at all these alphabets, right? ADO is a whole country. I can just go on and on about ADO. ActiveX is just so strange. It's some kind of Microsoft version of things like Java, Flash, OpenGL. Oh my God, so many things all at the same time. Microsoft went crazy in the late 80s and early 90s to come up with things against the whole world. They just did not like anything at all. They did not like Java. They did not like Flash when it came along. Just anything. We'll just make our own. And then the world of computer graphics, my world, had something called OpenGL, which just ran on any machine you played, like beautiful games. So Microsoft said, we'll make our own version of OpenGL. We'll call it ActiveX 3D and stuff like that. Active 3D. Okay, so ActiveX is a whole collection of stuff that they collectively call ActiveX. So in there, they made an API for databases called ADO. That's it. So ADO is now able to actually give you scripting language access as well. That's pretty much it. And therefore, all of a sudden, a Visual Basic programmer can run ADO calls, and that eventually becomes OLEDB, that becomes ODBC, then Microsoft will get you the data that you're wanting. That's it. So again, going back to my picture right here, you can just do, so now you can do Visual Basic here. So VB can plug in right here, and then all the rest can happen. Crazy, right? Just layers and layers and layers. Although that's a good thing, layers are good. Layers will slow you down because there's translation going on at every level, but so be it. But it works. All right, so that was ADO, specifically written for scripting language access to OLEDB. Cool. So this means practically, any programming language, which once again in Microsoft's world is just a few. These days you can count Lua. So Lua is a Microsoft-friendly programming language. They actually love it. They want the game people to use it. So things like Lua, C# for sure, although that's compiled, and Java, C++, C. So these are all the languages you can write all these calls in and make ADO calls from all those languages. Okay, so that's all part of Microsoft history. And then now you see OLEDB consumers, meaning what are all the applications, having OLEDB calls. So again, now there's the even bigger picture than that one. It's like, wow, all this plus a superset. Now what can we do in today's world? Like I said, scripting language people can make ADO calls. And then ADO calls can just stop right here. and then they can do all these, file indexing, query processing. In other words, it's like a shallow version of databases. So you can do like email processing. So apps can directly communicate using Ado, or you can use ODBC and get to it. But then more importantly, if you want to go to actual hardcore databases, you want email servers and so on, then Ado would then make calls to OLEDB. This is what I just now told you a couple of minutes ago. And then OLEDB eventually makes calls to like ODBC here. So they're all like depending on each other, okay? And so here we call them data providers. And so data can come from email serving, SQL serving, database, whatever. So any third-party vendor, all they have to do is implement ODBC, and then they can also be part of this Microsoft ecosystem. That's pretty much how it all works. Anything that runs on any database that runs on Microsoft will have to have ODBC, otherwise there's no way to get to it. No standard way to get to it. Okay, so this picture is like a summary. And then you still have Ado.NET. So the last step was to make a .NET version of Ado, and then there's Ado.NET. .NET is actually a fascinating thing in Microsoft's history. It was pretty much like a come to Jesus moment. It was like a almost survival thing that they had to do. It's like OMFG moment. This happened in the 90s, in the mid 90s, roughly, the mid to late 90s. Microsoft realized this big thing called the internet is completely going to come and bury them. Yeah. So not yet. Hold on to that thought a little bit. I'll get to that. Not quite. It's not like that. It's more like this. So in the early 90s is when, mid 90s, 95, is when Java came along. So CJ is absolutely right. So what happened was Java was a huge threat to Microsoft because Java's slogan was the network is the computer. So what they meant was, to hell with PCs, you don't have to pay Microsoft money anymore. Just get any Unix machine you want, including Linux machine, or buy a Mac or plug them all together. And Java runs on all of them, and you'll be free from Microsoft's death grip forever. That's basically Java's promise. Then Microsoft, obviously said, oh my God, we hate Java. So they try to make something weird called JScript. JScript is Java, which they hacked and made Windows-specific calls, do all the Windows services. So if you then, it looks like Java. Therefore, if you made a JScript program and you compiled it, then you're basically stuck because that program is not portable anymore. It just runs on PCs and it'll fail on a Mac. Then Sun said, to hell with this, because we own Java, we trademarked it, and one of the main things was it was the right ones run anywhere. So they went to court and said we want JScript to be stopped. And that's exactly what happened. So the court said Microsoft cannot support JScript anymore. So I'll just show you, okay? It just says Sun Microsoft JScript, lawsuit or something. Oh, okay, you can try this. Okay, so Microsoft Virtual Machine, Visual J++. Actually, not JScript, I'm going to say Visual J++, okay? Because they called it Visual J++, just like Visual C++. But then Sun said, to hell with that, you don't own that, so you're not allowed to call it that. It was definitely a lawsuit. And then, antitrust like this, just read about all this. So in the end, Microsoft could not get what they wanted, okay? Then they did something so weird. They hired someone called Anders Hellsberg. So Anders Hellsberg used to work for Borland Corporation on Turbo Pascal, Turbo C, all the amazing Borland compilers. He was basically a programming language guy. So then Microsoft said to him, that's what happened. Microsoft said to him, invent a different language, and we'll make it like our language. It's a Microsoft language, but make it be like Java. Sadly, C#'s hello world, class hello world, curly brace, public static void main, system.out.println, hello world, semicolon, close curly brace. That was C# 1.0, believe it or not. I'm not kidding, okay? So they pretty much ripped off the Java syntax 100% and then made it compilable and runnable only on PCs. So that is really what happened in the world today. And that could not be, sued because, it's their own language. So then Sun had to be quiet. And that is really what happened. So now they have something called Common Language Runtime, C# CLR. So Common Language Runtime is almost like an Uber virtual machine that can run Java bytecode and also all kinds of other things like C# and other languages. So they almost made Java like irrelevant. They made it like obsolete in a way. That's really what happened. But then it was pretty unfair the way it all started because they tried to kill Java and then Sun sued and Sun lost, Sorry, Sun won, and then Microsoft came and made Sun lose finally. And then Oracle dealt the final death blow to Java because Oracle then purchased Sun And Oracle basically threw it away. These days, no browser ever, none of these four browsers run Java applets. For a while, I could show you anything right here. It used to be like Flash, JavaScript, etc. Okay, but Java ran it all on the applet side. But then it got so badly screwed up, the implementation and the bugs and everything, like the hacking. And so now it's a security risk. So therefore, applets are not allowed to run. Even if I go on my PC and allow some site to serve me applets, the browser will not run it. I have to pretty much download the applet jar file myself and run like on the command line applet viewer. I've got like applet viewer. So applets that used to be so ubiquitous and so cool now basically just went away. That's sad. So I watch Java, pretty much like just die off. Although Java is pretty strongly alive on the server side, so don't even get me wrong. But then people don't interact with it directly. Okay. All right. So that's a lot of history. But that is where this all the com all is coming from. So this .NET is what I was going to tell you. Okay, so then Java, came and Java went, but the internet was still getting bigger and bigger and bigger. And so even if Java was not a big deal anymore, the world was actually, be able to run things off of web servers. They're all services, I can run my database on a cloud or something. It was not called cloud at the time. But you don't need to have a PC. The PC, whatever the PC could do, Google Docs is an example. I need Microsoft Word for my resume. Well, I can just go to my G Drive and just do it on the browser. So gradually they realized they're almost going to go out of business. So that is when .NET was born. So then .NET is a whole reimagination of the entire Windows framework as a whole service-oriented architecture. So now it's up to, I think, .NET version 4 or something. I don't even keep up anymore. But you can just say .NET, you can say service-oriented, or you can even say component-oriented, anything at all. .NET components. Say .NET components. Yeah, they totally reinvented themselves in a way. .NET components. And then it became successful. They're still around. And now it's much easier to actually update the Windows, so it's up to Windows 10 now. And everything got better actually because of .NET. All right. So these are all cool things you can go read up on. And then C# is heavily, behind .NET, although like I said, many other languages are also supported. So that's what it is. And yes, .NET can be ported. There was a project called the Mono project, the .NET Mono port. Except Microsoft actually did not like the person who actually tried to port all of .NET to the Linux world. That's what it is, like right there. But then I think he did succeed. Yeah. Okay. Very interesting. Okay. So I have a question for CG. Like, why the heck do you know all this? Like, how do you know all this? I see classified. Okay, interesting. Yeah. So moving on. That's fascinating. I don't know what to think of that, to be honest. Okay. Because I don't know how much I like it's not that I hate Microsoft. I've just lived with them, the whole time I've used PCs. So I have a love-hate relationship, okay? I have a PC as we speak, you can see. That to me sounds like a deadly embrace. So Microsoft has a strategy called embrace and extinguish. I'll give you a hug, but I'm going to kill you. I'll give you a death hug. I'll squeeze you to death. So it seems like that to me. In other words, if Mono was like out there, competing with .NET and saying .NET is amazing, but you can run it on your little Linux Raspberry Pi, then the obvious thing that Microsoft is going to do is just buy them and basically just bury them. I'll pay you to do nothing, just go home. It seems to me like that, okay? So sorry, I'm a little bit pessimistic. I don't buy that. Anytime they go and buy something, whether it's GitHub or Linux or Python, it's almost like, well, what are they going to do? How are they going to kill it? This is the question that I would ask. Sorry. Okay. So then moving on, .NET, you can tell, right? I tolerate Microsoft. Because I've been around for too long to watch them kill businesses, okay? There's something called Windows Inc. You can go look up on that. Other people invented Windows Inc. And then Microsoft gets a demo of Windows Inc. and then calls it Windows Inc. And then the Windows Inc. people, the real Windows Inc. people, would actually go out of business. I mean, it's like serious stuff. That's what they do. All right, how is all that connected here? This is because of this. There's now a .NET API. .NET has APIs for everything in the world. It's all of Windows. So they do have database access APIs, which I'm going to show you. All right, so therefore, today's world, how do you interact with databases? You can do component-based programming. You can have it all nicely modular. Then it's all distributed, heterogeneous, and all this is true. Highly modular. One word to replace all of this is just modular. You can plug and play, mix things together. Manipulate any type of data using any combination, any network, any operating system. Again, same thing, it's highly modular. It doesn't matter. It's almost like services, okay? .NET is a service-oriented architecture. When you call every little piece of a program a service, And the services simply send objects like JSON to each other or XML. It doesn't matter what the service is written in, or what type of network the service is running on, or not even what OS is. It doesn't matter. And definitely the programming language doesn't matter. So you have this mixed language model in the world where you can just simply base everything commonly on data. And as long as you know how to send and get, you're all set. It's a data-oriented world. That is what Ado.net is, okay? So Ado.net is a .NET port of Ado. And Ado already did like a lot of things, but now it's more component-oriented. That's all it is. So I'll show you this picture. This is actually very cool. Okay, so Ado.net, you can use C# or Visual Basic to actually log on to a database and get data and then log off. Then you have a disconnected memory resident representation. So I can go to, for example, the student database at USC and do a query for all the 3.5 to 3.8 GPA students, and then have all that table in my memory in my C# program on my PC, and I'm not logged onto the registers in GRS anymore. That is called a data set. So data set is simply the collection of all the rows and columns that you get from a query. But now I can run for loops on my data set. I can modify it. And you can even log on back to the original database and update the tables. So you can do part of your data, processing using like C#, for instance. And then it's all heavily XML based. So one of the advantages of using data sets is this: if nothing else, you can use C# to log on to a database and get a table, maybe the whole table, and store it as a data set. But now you can write a for loop and dump the entire data set as a .xml file. So now what you've done is taken that binary data table and fully made an XML text file. You can go and look at every field and every column and every row. Then maybe you can even delete the whole data table. You don't need it anymore because now it's all XML. So those are the fun things you can actually do with Ado.net, okay? Okay, so this data set is all XML in memory, and so it's pretty easy to dump it out. Okay, this is the part about dumping out. You can actually persist them as XML documents. It means it's one way to translate pretty old, like 20, 30-year-old databases to something that's XML and JSON. That's useful. Okay, so that is what this picture is. I'm probably going to put it up in the next tab so it's easy to big and small. All right. So once again, at the very bottom is sitting your actual binary database with all your, encoded binary data. And then in the end, there's ODBC here. So regardless of what happens up here, you still have to go through the bottommost layers that Microsoft still continues to support. But this part is about ADO.NET, meaning this is like a replacement for all the other colored wires that I had here. So what if you could not need all those extra things? What if you don't need ADO? And definitely what if you stop using like all of this? So what is one direct way I can get to it? That is exactly what this is. Okay, so now it's ADO.NET. Okay, think of Visual Basic as an example, or C#. Okay, here's what you do. It's in so this whole thing is in layers, this whole API access. So you have a data adapter, a data reader, data command connection. So in the end, you have a connection, okay, just like JDBC. You need to connect to your database. These are all these API calls. You make these API calls, okay? So the calls then go through all these layers, eventually become a real database connection, turn into SQL, and get results back. Adapter just simply means, suppose you have a table that has some, like two columns of floating point data. I want complex numbers. I'm like an electrical engineer. This adapter can take those x comma y and turn that into a plus ij or something, meaning make an actual complex number. Just very simple data mapping transformation. So in the end, I'm getting data the way I want, meaning the application expects data in a certain way. So we call it a data table collection. So in a data table collection, this is like the list of all the actual entities that actually make up the database. It's a separate piece. But then this is where the actual data is for all those pieces. Each piece is called a data table. It's simply rows and columns, okay, and even constraints. This all looks like SQL, but there's no SQL anywhere. This entire thing is XML based, which is why now after I do this, I can write another program that just throw all this away and take all of this and actually store it on disk as an XML file or a series of XML files, one per table. And maybe even make the entity ER diagram like an XML file. So I'm now I've XMLized everything that was here. Then we don't need this. You can destroy the drive if you want. That's the idea, okay? So Ado.NET absolutely is very modern. Nothing like bad to say about it. It's a good idea. It took like a long time for them to get to it, but then they're able to get to it. And the whole world can use Ado.NET. I have like fat books in my office. I don't have them here, but I'll just say you and I'll show it to you. Okay, I'll just say sample VB Ado.NET app. Then you can actually see it. Sample Visual Basic Ado.NET. I have read books. They're all for some reason fat red books, like 500-page books. all in my office. Oh no, I missed my books. So Microsoft's own tutorial. Okay, we'll just quickly scroll through, okay? I want to show you code. Okay, this is all just some UI that you fill. Hey, wait, because it's Visual Basic, they're all oh, there it is, form based. All right, so then you can actually start to see, like all of this. Yeah, schema. Yeah, schema is really just, another name for metadata about the columns and the tables. Okay, so I do this SQL client. Okay, what can we quickly see? Message bug. This is all mostly UI, okay? A lot of UI stuff. And then somewhere there's going to be a database connection. Okay, so then this is where the actual SQL comes in. So in other words, you're actually poking SQL commands through this whole Visual Basic interface. Oh, how do you scroll? Okay, I'm trying to go here. Yeah. Then there's like all these SQL commands. You can go through it afterwards. But this eventually what you do is you actually make a real SQL command. Okay, this is where the database connection actually happens, okay? And that command that you made, you fill the command with little pieces. You literally execute it. And then you'll get your response back, okay? So close the connection. Then when you get the response back, that is when you get a so-called data set. Then you can simply iterate for the data set. I think we should show like different languages. So that was like Visual Basic, right? But C++ might make it like more straightforward. Again, driver, nothing here. You can do C sharp. Just Google all this afterwards. I'll try C sharp just for 1 minute. If not, we'll move on because it's not important. Okay. So sample C sharp 8.net. 8.net DB access. Yeah. Okay. It's a different one. Okay. I'll tell you about link another time. But there it is. Okay. So this is like C sharp, right? Looks a lot like Java. So class static void, like all of those main. And then see, this is SQL right there. So you literally make a C sharp string, and then the string is actually a SQL command. So in the end, you're just wrapping SQL through like so many programming languages and layers. That's all. And there's your connection. Okay. So then it'll actually log on. In JDBC, if you know JDBC, it's basically exactly the same thing. JDBC will also have, a string that is SQL. It'll also have a connection object. Then it'll have a statement object. Then you would do something very similar, connection.line, and then like this, just simply execute. Isn't this go? Yeah, but they protect against all that, absolutely. So hopefully the backend that is receiving the SQL engine, which I'm going to talk about in performance tuning pretty soon, will hopefully reject like crazy statements. That is like standard database protection. Hopefully there's nothing new that you can do. In other words, anything you can do directly on the command line would be all you can do from here, nothing new at all. It's still going through the same engine. It just makes the access easier because now you can do like see stuff like this. You can do while loops, okay? Loop try. Yeah. Yeah, cool. So all of them ultimately look the same. They're all doing the same thing. There's a statement, there's a connection, there's an execute query, and then you can go through the results yourself. Okay, that's all 8.net. Good. All right, so you can know the things that I showed are all compiled into all of these are a video game if you want to think like that. And okay, so what else? ODB types of objects. Yes, talked about this. I told you this. Showed you this diagram. Showed you that. And then what else? Right. This is where we stopped. This is where we were. Showed you that. Right. So then this I already told you, but now we can tell you a little bit more. JDBC. So as an alternative to all the Microsoft stuff such as RDO, ADO, Jet Engine, ODBC, whatnot. Instead, through Java, there's only one interface called JDBC. It's pretty big, it's got like lots of classes, lots of methods, but it works. Sun supports it. Oracle supports it. So Java is object-oriented, all of those too. From day one, these are all the things they had. They had a whole bunch. It was a long list of words. It was all like basically buzzword compliant is what we call it. Okay, buzzword compliant. So JDBC is just one of those thousands of classes that Java comes with. Java has almost like 6,000 classes or something. They're an API for everything, right? Even things like socket APIs, TCP IP, you can just do it all with Java. So JDBC is just specifically for data. Yeah, so this is the magic of it, okay? As long as you know where the database is located, plus username and a password, of course, then you can log in. I have a sample that I can show you right now. Advantage is that people that know Java can instantly become like database programmers. You still have to know SQL, obviously. Okay, so then you can, do SQL through Java, and then you don't need to do ODBC calls, just use JDBC. This is Java. Okay, this is what JDBC looks like. Okay, again, it's like really fast. Many years ago, I actually used to give a homework, to students, and they would write Java code to actually log on to their own Oracle database. It's pretty cool, but it's so small, right? This little thing. Start with public static void main. That's what it is. So make a homework object. The whole thing is called homework two. So make yourself an object like that. This way you would put in the actual username and password, okay? And this is the URL. So as long as this is somewhere in your local network, you can log in, and then you say get connection, and then the get DB connection is actually up here. This is the one that is gonna do the register driver SQL exception. This just simply receive and log in. This is the main thing. You ask the driver manager for a connection. So literally you say, for this username and password, give me a connection, and everything is then happening with the connection. The connection will then turn into a statement. So then you have a connection, and then after connection you can add extra things like statements and so on. Select here, a connection, then you can make a statement. You get a query. Then this is the main thing, the result set that I told you. But there's no Java, okay? Okay, so once you have a con from the previous, thing, that con, you can now use that con to actually get a statement. Here, con is called mycon. So mycon.create statement. Now you have statement. That statement can now actually have SQL right there. That statement dot query can have SQL. And when this line runs, you will get results back. So this is your table rows and columns that you're getting. And then you can do an iteration through this. There's an iterator for that result set. So this is a little bit piecemeal, but I think I have a whole link somewhere. Where's that? Right? Okay. Oh yeah, this one. I just will look at the whole point, the whole piece. The piece is here. Tutorial point. Like that. So again, I'm going to go fast, okay? It's easy. You just need to know like where to log in, and then the actual credentials, and then public static void main as usual. These are the two main things: the connection and the statement, okay? And then the results, of course. So then there is the driver's name, and then create a statement. So this is the actual SQL. Select ID first line, and then you're just looking at employees, okay? There's not even a where condition. But that's the neat part though. So once you make that statement called create statement, that statement would have an execute query. That SQL is literally being executed. This is where all the magic happens. Then you get a response. What do you do with the response? This is iterators like dot next. Just keep saying dot next, and then you will actually get every single row is given to you. And because you know what is in the row, you know things like ID, first, last, you can just simply say get, okay? You can tell RS, give me the ID column. Just literally get the access, and then you can print it out. Yeah, that's a cool idea, right? I'm going to think about that, okay? Because I also thought that. Maybe you and us, like, a little piece of like the last homework or something. Because it's a very neat thing to do. It actually works, okay? Maybe you can take the SQL that you wrote and then put it in like a local Oracle installation which runs on PCs and Macs, and write a very small Java program. I can even give you like most of what you need, but just go on Java, I can just compile it, and even on command line see if this works, okay? Because it is neat that you can query your own tables like that with one line, okay? This right here is just all the magic. SQL in, data out, and then Java access. Wow. CG wants to use ODBC. Okay, so just for you, CG, you can use ODBC. How's that? That's funny. You can use whatever you want. I'm pretty friendly when it comes to all that. Okay, just insist on one API. Yeah, I would hope that most people would use JDBC, but if you know ODBC better, you can use it. Well, maybe that's the reason you want to use Cloud DBs, learn ODBC. Okay, so then how does JDBC work? Okay, JDBC is not magic because ultimately, natively, it does have to either call ODBC, means you're going through Microsoft, or Java, now Oracle, can write their own drivers, just a straight Java driver. So they can do it in one of three different ways, okay? So this is a middleware. So maybe the middleware has an API, and then JDBC can just communicate with that API. So there's three different ways in the Microsoft world. The non-Microsoft world, there are two different ways because, that goes away. So many ways for JDBC to connect, meaning we don't have to worry about any of this. So the end programmers, people like us would just write this, and then it doesn't even matter. Like we don't know or don't care how all this actually runs. Does it go to a middleware? Does it go through ODBC? Did Sun provide their own drivers for this crazy database? We just don't know. But it doesn't matter. It just works. Okay, so that's what this was. Again, the public-facing high-end and this lower end, the back-end, so to speak. Every API has two parts, okay? The actual programmer part, which is the actual API application programmer part. And then the behind, the reverse part that says, wow, what does the programmer want? So you have to translate it. And then the native app would know, or the hardware device would know. Cool. Okay, so then this is just this notion of cloud apps, okay? All right, so when you have this notion of a cloud, and then the database can now communicate with any other server in the world, Then you open up the entire world of computing to the end user. They can just sit, on their bed with their phone, tiny small little phone. I can access everything in the world because I only need some kind of a local internet service provider. And I'm getting onto some main sites such as Amazon or Price Grabber or LinkedIn or anything. But then they in turn communicate to send results back to you. There's so many servers like all over the world, and they're never going to tell you what they are, and you shouldn't even ask. It doesn't matter. You magically get stuff here. And those are called services. In other words, this app, this one thing you think you're running, this one Amazon t-shirt you're buying, it's not just all running there at all. The t-shirt credit card order is being validated here. This is being used to get you like a tracking number, and this is being used to serve you the questions and answers, and then you rate it eventually, and this way your rating goes. And this is God knows what. This may be the recommendation engine that says what else do you want to look at. So there's so many things that happen when you're browsing Amazon. So the entire world of working this way is called service-oriented architecture. So it's all services. So what happens here is this could be a Mac OS server for all you know, but then all that you have to do is just send like a request and you get a response. And those are all XML or JSON. That's all you need to know. So therefore it frees these programmers, it frees all of us in the world really to just do the one thing that we're so good at. We just expose our service to the so-called API. So this TMDB, for example, so they can tell you anything about movies as long as you know what to ask. But don't ask them how they're doing it. It doesn't matter. They could even have their own database, obviously, okay? But then you will just simply access everything as if it's a service. The services are the best. Ha! Great question. Fantastic question. You know, there's a whole. It's called discovery. Okay. Yeah. Maybe after the break I'll tell you. So the whole rest, like all of that, right? Wow. Okay. So if you want to Google it, I'll just type it in. It is things like web services description language. Okay. And then it's basically something called UDI. The thing that I'm getting at is something called UDI, Universal Description Discovery Deal. This UDI. So UDI is how, when you actually make a service, you have to basically announce it like this, okay? So the service provider, so that's what you're asking. So how do you know like where to connect to? The service provider will not only make a service, but also make a registry entry at some public computers in the world. They're called UDI registries, okay? So the registry's job is to hold a list of every single service that everybody in the world can provide. Then when you, the consumer, wonders, wow, can I get weather data? Or I want to know how much a Bitcoin is worth. Is there a service for that? I want to go look it up. Then they first query the UDI to see if a service does exist. And if such a service does exist, UDI will then send you back basically the parameters that you need to actually exchange data. And then afterwards, you don't need the UDI anymore. You can just exchange data. That is the answer, okay? So the question is, how does the world know about this amazing service that you wrote? And the answer is the world doesn't know. You have to go and advertise. But thankfully, there are standard places where you advertise. So you advertise, and then somebody searches. So just like a little bulletin board message exchange. That's how it works. Okay. Um, I mean, neither. It doesn't do either one of those. It's what I told you, okay? So every service provider's responsibility is to go and update the UDI. That's like a message you send to UDI. And then afterwards, service consumer directly makes the UDI call. So you would not actually do that at all. If you did not have UDI, then your service consumer has to jump from God knows wherever. You have to just go like all over the place. Okay, that's crazy. So thankfully, the discovery mechanism does exist. It's called UDI. Okay, that's how it's all supposed to be. Cool. Okay, so all that is here. Therefore, because of this connectivity, you can now make Grubhub, for example, or you can make, even Lyft and Uber. Those are new services that could just never exist in the world before. Now I can just take out my phone, and then in 10 minutes, driver appears, and it's not a cab. It's a very different world. That's what this is. You can make all kinds of new services. You're writing a backend app that communicates with like all kinds of services, maybe even your own database, and then just expose that to some front end app that somebody downloads for free. And you have your whole world of internet e-commerce, service-oriented world. Okay, so increase customer satisfaction. So it's all true. Okay, so all this means the same thing. Okay, this all means the world is now service-based, and this is probably the very best way in the world to program, because I cannot think of a better option. Like what could be a better option, right? Except these days, already the better thing has happened. So then the question is, what are these servers? Are they all .coms, and what if they go down, stuff like that? But these days, pretty much every real service that we all use is all running loosely on what you call the cloud. It means that there are still servers and they actually have like URLs and domain names and so on, but they're all abstracted by this entity called the cloud. And then massive companies like Amazon, they run the cloud. So they provide guarantees. If you're Lyft, for example, Amazon will tell Lyft, we provide you like a 99.999, it's called 999% uptime guarantee. It means that much percent of the time that the service is active, it will not fail. There's only a 0.001 percent time it's going to fail. And if we go below the guarantee, meaning say the server actually goes down, people are not able to get cab rides, then Amazon refunds a massive amount of money back to Lyft. So that's called the service level agreement. It's called SLA. So that SLA guarantee is why Amazon is able to basically, make billions of dollars, because Amazon then hires like all kinds of, data engineers. And in your contract, it probably says, we'll wake you up in the middle of the night. You need to fix if there's some problem. So, if you agree, we'll give you a job. That is how the SLA is actually, honored by people like Amazon. And then when there are outages, it becomes big news. Okay, so massive services fail. And that could be actually dangerous. Somebody couldn't get a ride home and somebody came and stabbed them to death. So it's big things ride on a cloud. But if the cloud is backed by Google and Microsoft and Amazon, then hopefully nothing bad would happen. Okay, so that's the cloud stuff in a nutshell. But we'll do much more about clouds, I think. We should do all that in part 2. Why I said something about e-commerce, right? Exactly. So why bother with all these services? It's not so you can look up weather. It's mostly to make money. So I just went to Amazon.com. I mean, every little thing here, right? There's a reason why they put up smart plug, because I probably looked at it. And so they're just crazy. I looked at the book recently, and so there it is. I never went to Amazon, by the way. I looked on Facebook and other places. But then they all send data to each other. So there it is. It wants me to buy it. So everything that is in here are all coming from different parts of Amazon. We have no idea where they are. All these, like even the shop now, probably something else is going to happen. Recommendations come from somewhere else. All this come from somewhere else. But to us, it all looks like it's just running on this browser. Amazing. My shopping cart is always empty, but if you go in there, then all the results are coming from somewhere else. Everything is coming from somewhere else. Okay. Middleware. So this is a useful thing to talk about, right? Middleware part. Now what happens is, what if there was another machine between the backend and the database? In fact, I have not quite even mentioned that. Suppose it's your own database. I never mentioned that connection, because you can do extra things called CGI, Common Gateway Interface. So we should have some fun with that. Okay, what does middleware mean? Meaning, how does the web server, whose job it is to just serve web pages, deal with data in the first place? How does that happen? Web server. If the world of e-commerce data all that didn't exist, the way Tim Berners-Lee envisioned the web is the initial server that you connect to has local HTML pages, all about nuclear research materials and what. Then I browse some material science article. I like something about solar energy. I look up some solar cell article. But that article has a hyperlink that is pointing to some other server somewhere else. All I have to do is click on the link. Then my client says to this server, please send me the document. And then my page updates, okay? Just classic simple web browsing. That's really all it is. So the initial www was pretty much mostly organized around this model of just browsing documents. So I don't have to mail that scientist and say, can you please send me that paper? It's all just live constantly. But they did realize, even like back in the day, www 1.0, that at least a part of the web server needs to have a mechanism to run pretty much things in any programming language, like a Python program or a Java program or a C program or Perl program or Ruby program on the command line. The client never sees it. But then when the program just runs, that program can then go to a database, for instance, then get some data. Perl, for example, has something called the Perl DB module. So I would write a .pl Perl script. It's called the Perl programming language script, which knows to log on to a database. So I send in my username and password, and the client just sends it off to a web server. It doesn't do anything. It then calls this Perl program and says, you run. Then Perl will then go in the database and then do what I wanted, want some data. Then Perl will get the data. And Perl can even format HTML. Perl has a print statement. You print HTML, and then you put your data in the middle, meaning you create a web page dynamically, and then give it to the server. The server would then send it to you, and then it just updates, and you've got data. That thing that I just now mentioned is called the Common Gateway Interface. It's called CGI. CGI. So CGI was a mechanism where a part of the web server could be configured to run scripts, as long as the scripts are either inside the CGI bin directory or some other directory that you configure in the web server configuration, but not this part of your machine. So I don't have free access to run anything on your machine. That's not what CGI is. It's a very sandbox environment. But within the sandbox, you can do extremely powerful things. Perl also has obviously, like internet command, so I can actually go off on the server. This can be a Java program. This is where the whole backend Java comes in. So I can make a .class.java file, which I run from the browser. And because it is Java, it can do again connection, TCP/IP connection to any machine anywhere. And even do robot crawling across 1,000 machines and get all the agent programming and get all of that and then come back and give me data. So you have a very powerful backdoor. It is called CGI. A middleware is not CGI. So CGI is one form of middleware. It is middle because it is between the web server and in a database. But an actual middleware is what is called a web application server. So now this is an evolved idea. It's a different idea where it can be a separate machine, and then all this one happen. The web server would then forward the request to here, and that will then do the translation. This can also print HTML and so on, like template-based programming. These days, when you do a Flask application, for example, or Express or something, it's not this really. It doesn't run on a separate machine. It runs more on this, but it's a little better than this. Some kind of hybrid between this and this is what like a modern Flask application would be. Right there, okay. Okay, so Yash said something. Why don't the big companies cache most of the data? Well, they actually do. Yeah, they do. There are all kinds of proxies, okay, that cache almost everything. Even CNN can actually cache, not the headlines articles. Yeah, they absolutely do, for sure. But good question, though. They should. Right. Exactly. So Redis can constantly be updated to maintain the latest cache. If the cache is invalidated, then you can go and basically update your cache and then keep serving that. Yeah. So caching is like a big deal because it gets your data fast, and then also on the server side, frees up the server. You don't have to keep retrieving the same document over and over again. If you have a lot of RAM, that's exactly what you can do. You can serve things even fast by just keeping lightweight data in the line. Sure. That's the first kind of NoSQL database, right? All right, so moving on here, connectivity. Therefore, I'm going to tell you about both kinds of middleware. One middleware is just simply CGI. The other middleware is actual machines, okay? All right, so the CGI, the common gateway interface, is simply called server-side extension because you extend the web server to do more things than just serve web pages, okay? Okay, yeah, again, like I said, this is in two different pieces, two different kinds, actually. The client doesn't know. All right, so the client just wants what looks like HTML. It makes a request, and server gets it. This is standard, client-server programming. But this middleware, whether it runs as a directory here or whether it's an independent machine, has the same purpose. The purpose is to get your data. So then, say it's a Perl program or JBoss, an actual application server, middleware server, will then run the SQL command and get your data, and then format as HTML. You'll get HTML. Cool. So that's a middleware picture. And the CGI, it's sometimes called CGI bin, 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 because it's a bin binary directory. So the CGI bin directory, or just called CGI, they both do the same thing. So the client is here, your phone is here, the phone makes a request, somehow go all over the internet and show up on the server. Then the server says, I don't know what this is, it's not an HTML page. I'm going to run a CGI bin script. What I mean is, I actually threw my link. So I clicked on something, and then the request that got submitted has the script name on it, and it has username and password. So it's all passed off to that little script there. And then that script can run. And the script can do whatever the heck it wants. Say it's a Perl program, it goes all the way until the Perl get data. And maybe even filter the data. It can do some little extra thing the SQL didn't do. And then finally format it all as HTML. You literally print HTML and put all this data that you got in the middle of the HTML. As if it's a table, you make table HTML. You send it to the server, and you will magically get a table. The table is filled with data. But the thing is, there was no HTML already stored with the data that you wanted because they have no idea what you're going to search. Amazon, I can search through 1 million items, right? Probably 10 million items. So all the HTML that we saw when I went there was not sitting in here. It was dynamically generated. That is the whole point. When I tap on something, the same thing happens and I get new data. My page refreshes, right? It's basically amazing. Wow. I can serve anything through HTTP. That's what this is. All right, so the middleware, one last time, can be little scripts or they can be separate machines, okay? I should just show it to you. What if I do this, okay? I have my own little toy example. I have little examples. What if I, okay? So right in the same bytes server, I have an area, right? So in there, I have a little CGI directory, and I have just the most basic, like test.php. I could have made a link for it, then you click on the link. But that is running, this is not the web server, this is separate PHP running, and it's bringing all kinds of information about the web server. Actually, I think I even have a Python example. This one. Oh, cool. Okay. So that's very neat, right? So imagine instead of this, I got you the whole internet. I got you terabytes of data. It's totally possible. So then you think how like, what is this? There's no way you can look up the source, right? Because, it's just going to show you that. But what is it actually doing? So how did it actually, like, what is running in the backend? In other words, what is the source for h.py? You have to actually have backend access to it. So I can very quickly show it to you because it makes sense. So what this is all telling you is you can write Python programs, Perl programs, Java programs, C Sharp, whatever, that will actually do very powerful things. So right now I'm not doing any powerful things. What is Ngrok? Cool. Okay, I'm going to actually, okay, do this. Okay, so this is all obviously what the world doesn't have, right? So the people that have access, they're the ones that support all these scripts. I'll show it to you. I'll actually cd to a public HTML, then the CGI directory, just straight go there, okay? So because I'm not showing you what else is on there, I'll just do a cat. Okay, it was that simple. What happened was, see, it's literally a print statement. You have to print this header, otherwise the browser doesn't know what to do with it. The browser won't do this unless you print exactly that header. And not only that, the header must be separated with actually an extra line. That's what this is. So if you mess this up, this won't work. It'll say internal server error. You'll get all kinds of errors. But I know how to avoid them, so I made it better. You have a blank line, and then you literally say HTML. You say head, and it went on head. And I say hello from Python title. That's actually up here, hello from Python up here. And then the H2, that's what this is, header level 2, hello from Python. And then for the hell of it, I'm importing the math module. Then I'm saying print dir math, so it gives you all the functions in math. But here's where I can go crazy. I can do some Fourier transform on some signal that I stored on this directory. Right? There's no end to what you can do with CGI, and the client just gets it, okay? It is radically powerful. I can log on to databases from here if I have access to it. So CGI is like the ultimate mechanism. And things like Flask, Gain, Express, all that is just simply slightly better versions of CGI. It's the same idea, okay? Get rid of all this. Okay. So then let's finish this up. Then we can do other things. Tuning maybe. Okay, so therefore now you understand exactly what happened. Okay, so my hello world.py program ran. I didn't do database access, but I got the math module. It's the same idea. When I'm able to make HTML, I printed HTML literally, still up here. You can literally print HTML and then put the data that you want. And I didn't format this, but I could have made this into H2 or something. So you are literally creating data for the client. And the client thinks they're accessing a database, which they are. But then you provide the format for it. It's a round trip, okay? You do something and you do something more full. But the HTML page that you saw was not just sitting there. This was not some static something that HTML. It was dynamically generated. I can even go and say, give me all the things to begin with the letter A. I can run Python calls for it. Python has almost like 90,000 modules. So I can use any of the 90,000 modules to get data back to you. So it's like super powerful. Node, on the other hand, JavaScript can also run right there. Do you know how many modules Node has? Can anybody guess? Python has about 90,000 libraries. In Node, they're called packages. How many do you think there are Node packages? Anybody? Rough guess. Rough number. Just throw out a number. How many Node modules exist in the world approximately today? Python has 90,000. That's a good guess. I'll tell you, 1 million. Exactly. 1 million. Oh my God. 10 times Python. Welcome to JavaScript. Okay, so on that note, going on. CGI is exactly what I just ran, okay? So there are basically 3 or 4 ways to do it, okay? One of them is to go in the CGI directory, through your link, and run the .py literally if you have permission. That is what I'm showing you here. It's called the CGI mechanism. An external program was h.py. You can do database access. That's one way. The second way is slightly more refined. So this is like things like active server pages. Microsoft has something called ASP, which is again a script that you can run in Visual Basic. And that script is going to run, and the script can then do like ADO.NET calls and then get data back to you. And the script will have the same HTML, and you can go back. Or Java can do this, and it's called Java Server Pages. It's called JSP. So JSP is then sitting here, and then it looks like HTML, but it's actually templated HTML, meaning pieces are missing. But inside, when I make a call, the JSP can then kick off actual .class.jar file access, which can then do Java, the code that I showed you for homework 2. Can do here, log onto a database, get data, format it all back, meaning This looks like HTML, but pieces are missing. Then your Java program can fill in all those templates. It's called templates. When you fill the actual template, it might say the word name. You might put your real name into let's see, and then that will come back as HTML. That is what API is. So you have Java APIs, so like active server APIs, what Hawkins APIs. But they're a little bit nicer than CGI. They're more like object oriented. They're more packaged. Okay, but they're the same idea. The third idea would be a separate machine called the middleware. Okay. So then this Perl CJ, I talked a lot about Perl, right? So how does Perl interface with the database? Suppose instead of Python, I ran Perl. What did that look like? I think we have Perl installed. I'm not going to do it now, the database access, but see, Perl is running. So I could have replaced h.py with an actual Perl script, and then do all the things that Perl can do. They all run on the command line, by the way. So they all just run. Therefore, anything I can do on the command line, on the back end, then I can actually send stuff back to you as a web page. How neat is that? So that's what that was. I'm going to show you is the Perl DB, what that looks like, okay? Okay. So Perl DB is like this. It's going to look so familiar to you because it'll be a combination of Perl and also SQL. All right, imagine this SQL was already done, okay? So somebody, just like your homework, you made all of this and you put data into it. Now what can Perl do with the data? You can do this. Make a Perl script, use the module, this is called DBA module. You literally tell the module as a method called connect instead of dot, we use arrows in Perl. And Perl variables can have dollar signs. Connect, again, this is the URL, that's the username password. That's simple. And then you get a handle. Handle is like an object, like a connection object. What do you do with the connection object? You have a statement. The statement is called prepare. In prepare, literally poke SQL. Wow, this is SQL string line. And then you get that, right? Now we call it a handle. And that line, you call it a key. So then the handle would come back. This is statement, key statement. Then you say statement execute. That one line will go in my database and query come back. Then I can use Perl looping. So while at row, like this, just do looping and just print using good old print statement. And then I'll get my results. It's like magic, right? Holy crap. What all this means is programmers today have access to different languages. Perl, Python, Java, JavaScript, any language at all, and SQL. So then you can do the best of both worlds. You don't have to do all of this in Perl because that'll be a pain, right? Just write good old SQL. SQL is very powerful. And then it can do its thing, and then you send results back. All right, so then this way you print HTML. So look at this. You're literally printing HTML, okay? Body, all of this, and then this will all go back to the client. The client will just, this is the same thing that I did, they know to separate with a little line. If you delete this, the client will get garbage. It'll say internal server error. The header, which is the actual header that the server returns, must have a blank line between that and everything else, okay? So just make a note of that somewhere. That extra new line is so damn important. All right, so that's how Perl works. It still works today. Database access. All right, so Corba, you're basically writing rules in Perl. Yeah, sure, exactly. That is correct. Instead of a rule, you can even say the word code. You're just writing code in Perl and Python. Perl, by the way, is PERL. There's no A, okay? Practical extraction reporting language. There's no A. Yes, so writing code in Perl or Python, whose job is to basically take a SQL query and then run it, and then get the results and do some extra calculation or iteration and just give it back to you. Yeah, that's all it is. It's all string-based, right? Shocking. Because SQL is a string, and also the HTML that I print is also a string. Look, oh my God. Or you can send JSON or XML. Okay, so then what about Corba? I talked about Corba. This is not about middleware, but more like how do Unix machines interchange objects with each other. It's a great blog that you should read at some point, okay? It also talks about security. So again, the client makes a SQL query, and how do you get the data back? We call this. This is straight. You're directly logged onto the machine like an IBM mainframe or something. But then what if you have levels of interaction in between? There are multiple clients, multiple servers, and then this subsystem. So let's move on. Okay, this is the part that is cool. Your phone makes a request, and then what does the server do? Like, what is this? Like this, so it gets more and more detailed. This is what I just now showed you. You can make a Perl CGI script or a Python CGI script, and then go and do something with the server. And then this goes on into more detail about how it actually works, okay? So Corba, so how are all the messages exchanged? In other words, how would the RDBMS server actually give me data back to my Perl program? There's some Corba that is being used to do the object exchange. So in other words, how does the Perl know what the results are? That can be some Corba right there. So Corba is used like all over the place, and you can go read this, okay? It's like a big blog about all of this. Okay? And then what happens if things go wrong, If you like security, then you can go read this. Some extra fun FYI. All right, so I told you about CGI scripts, then I told you about JSP and ASP, specific templates. There's also one more thing called a server-side include. A server-side include looks almost like an HTML file, with some parts of it missing, meaning that they're supposed to be filled in. It'll say things like dollar name, okay, and then somehow they get filled. So those are called server-side includes. Let me just show you that. They're basically extra tags that you add onto an HTML page. But those tags look like comments. So if a client does not know what to do with it, then it'll just ignore it. But in those comments, you hide commands for the server. And the server knows what to do with all those commands because they're not comments, they're actually commands. They're called server side include. So what is an example? It's stuff like this. This is the email tag. Okay. These tags are all what you can put in there, okay? So like that, okay? That's a comment, right? That's a classic HTML comment. All this is just a comment. Therefore, a standard client would ignore all of this. But the server, if you ask the server to send you this page, the server won't just send you this page so you can ignore all this. Instead, the server would actually execute this part. Wow, there's an if statement. So you can hide code, you can hide actual execution code in commands. Those are called server-side includes. It's crazy, right? That's what you can do. Okay. So you can hide database access code. You can do it. Hide many code. Hide meaning the server would then execute all this. Wow. Then your HTML page is much more rich, okay? Okay, that is called server-side includes. And for connectivity. Right. So then Java, is its own little country. I only showed you JDBC so far, where you can straight go to JDBC. But Java on the web can do many more things from inside a browser. If the browser lets you, I can make database calls straight to a database if I could. Or Java has something called sockets programming, where from the command line, I can run a Java program that can start interacting with so many servers on the web. I don't even need the browser at all. A command line program can do it. For example, I can use it to communicate with maybe a bank, even if I knew the bank's IP address or all of that. Straight machine-to-machine connection, okay? So straight connection. Servlets are what run on servers. Again, this could have been a servlet. It would have been a servlet. So servlet's job is for the server to run some Java and get some data back to you. Or there's something called remote method invocation, which looks like this, but it's not. This means if you give me permission, I can run actually on your operating system, in your memory, in your process, some function. Wow. It's called remote method invocation. Highly powerful, highly dangerous. Say I have access to a microscope somewhere halfway across the world. I can use RMI to actually control the microscope. I don't need anything else. No web server, no middleware, no CGI, no SQL, nothing. I'm just straight turning some machine on and turning it off if I want. That is called RMI. Corba, Java can do that as well, where you can communicate with any device in the world. You can access, they can exchange objects with you, but Corba is the object format going back and forth. So Java programs can read and write Corba objects. Java is amazing, right? Finally, Java can do one more thing, which is you can make an agent program in Java. But the difference between this and any of this is all of this will stop running when you turn your machine off, because your process ultimately is responsible. But agents are like crawling robots. They can continue running across the internet even if you log off. And then you can make the agent write to some database on your behalf. Then the agent is collecting data. It can crawl from site to site and actually fill up your database. But you're not logged in to see that. It's magical, right? That is agents. So Java can do like a lot more things when it comes to data than just simply JDBC. That's just one of the things it can do. All right. So then what can the client do? All this, everything that I ever said so far, it's all just server based. I use Java. Oh, I see. Very nice. Okay. Well, feel free to add on to what I said or challenge what I said. What can the browser do? Okay. These days, throw it away. Stick to JavaScript. Seriously. In the past, there used to be like a Flash, right? Flash plugin. So as of this beginning of this last year, 2020, I think, basically Adobe said RIP Flash, no more Flash. So Flash was a plugin that ran on pages. And Flash plugins could actually log onto databases. Flashes are pretty powerful. There was something called ActionScript. So the ActionScript language can make you do neat things from directly the client through a web server. But that went away. Likewise, ActiveX and Visual Basic, this all Microsoft stuff, would actually be some code that is in your page like this. And you click on something, and then that code can actually execute. But that can be very dangerous as well. So all kinds of virus, stuff, attacks happen. So these days it's all considered security risks. Okay. Java, sadly, it was a good idea. Apple, was a very good idea. But then it's also broken. The only game in town really is JavaScript, okay? JavaScript basically took the place of everything else in the world. There's only one left. And this is highly managed, the V8, like all these monkey, different engines, Spider Monkey, all of those, that all these different browsers run. They're pretty industrial strength, which means that as far as we know, there's like very little that somebody can do at the language level to exploit and take over your machine or crash the server or something. So these days, all of this functionality is replaced by JavaScript. And all that means is these things that I think I've shown you before, but I'll just run it for the hell of it, okay? This is data anyway. Say I have some data on a server. That's exactly what this is, actually data. So JavaScript, which is right here, is now letting me get the data. The data is literally here. The data is in the form of a URL, but it's data, it's JSON data. I'm able to get the JSON data purely through JavaScript and make a call. It's data. And then I can use more JavaScript to turn all these numbers into my little teapot triangles and actually put it up there. So this is what's meant by saying JavaScript is the only game in town. This is a pure HTML page from top to bottom. You can even copy all this and put it on my desktop, okay? It's simple HTML. You can even run this, by the way, if you want. If you're fascinated, take this link that I have and just run it, okay? I'm going to copy it. Then you will get the same thing that I get. We're just being served the JSON file. It's bytes the same, and then tilde city, and then tools, and then shem, xcm shem, and then run.html, and question mark, x equal to svg run length. I'll just leave it up here. But when I hit enter, something cool is happening. All of this actually got encoded like right there. So the string is gonna turn even more, but we don't have to worry about all that. So just ignore the extra part. In other words, all we need in the client is just JavaScript running, and I can get any piece of data in the world. So ignore all these, just only say that. That's it. Beautiful. Okay, now we come to the actual web application service. So what if you have middleware that is truly middleware? Now you have something between the web server and the database. So you have client, which is us, client, and then communicating with Apache, like web server backend. And then here's database Oracle. But then there's no CGI or anything running. There's no Perl CGI. There's actually a machine here, such as WebLogic or something called JBoss. These are called application servers. JBoss is entirely written in Java. It's a Java server, Java-based server. Then what happens is any request that you make for data would have to go to JBoss, and JBoss would do appropriate translations, even like transaction management actually, okay? And then get data from you. So this is doing a little bit of the work of the DBMS actually, and freeing up the DBMS load a little bit. It's doing all the client access restrictions and everything. So such a machine is called middleware, database middleware. So we'll say a few words about it. What does it do? It gives you all these services because you can log on to services. You would connect and query database from the web page. That's exactly literally what I just now showed you. So you, with your phone, can run some query here, but through that. I want to clean up a little bit, okay. Okay, so then, you can create dynamic pages because, again, what this is able to do is take the data and send back formatted HTML. There's all kinds of templates that are stored here. It won't give you raw data. If you want, you can get raw data. Otherwise, the data is formatted like HTML, and then you get HTML. So it's a service that it does. And then referential integrity. Yeah, this is also doing a little bit database management. So if you write some queries that actually go and delete data, then it'll make sure that foreign keys are also deleted. JBoss can actually do that. That's very neat. That it's almost like a mini, database engine. Except the difference is the disk is not directly controlled by that. It's not another copy of Oracle. It still has to talk to Oracle. Correct. It's a mediator. That's exactly right. Yes. But it can do a lot of translation. It can do a lot of database management as well, like I'm showing you. It can do, for example, referential integrity. And then authorization. So if you don't have access to anyone send the query to the actual DBMS. So it's a specialized server that interfaces with web services, such as databases. Okay, so any search that you're doing is also ultimately served through a middleware like that, okay? Because the search engine is actually running here and it has own all the search indexes. The middleware is what's coordinating the search with the web server. So it has that function as well. And the client just simply knows nothing, it's getting data. Cool. But then what is common to everything that I said is all the data is not statically sitting on HTML file somewhere. It's being generated on the fly just for you. It's dynamic data. Cool. So then a little bit more about these web application servers. So it can do authentication. Like I said, you run some SQL and then try to get data that you're not supposed to get. Then even the DBMS would not know what you asked for because the web application server can stop it. And then it can log on to multiple databases. That's actually pretty cool. You can make it log on to many different services, and so then it can pull everything together. I don't know what even this means. Ignore that. Actually, I know a little bit. One of those is actually called the ColdFusion markup server. Okay, there is something called the ColdFusion markup language. ColdFusion markup language. So ColdFusion markup language is something that runs on those web application servers. In other words, this holds what looks like HTML. Instead of this, just say ColdFusion. The name of the server is ColdFusion. So in ColdFusion, there are directories that have what look like HTML, but there are pieces that are missing, they're templated. When the client wants something, then ColdFusion's job is to then go and get the data and put in the missing HTML pieces, take all the extra stuff out, and send it back as pure HTML. So that programming to actually do all the access from ColdFusion. So what does it actually mean, right? You can use programming languages, and that is exactly what said this IDE is for running things on the ColdFusion server. By the way, you can use ActionScript actually, which is the programming language for Flash for doing ColdFusion stuff, because it all used to be owned by Macromedia. So Macromedia was the company that made Flash. They made ColdFusion as well. So it's pretty old stuff that I'm telling you. Let's actually Google it. I'll show it to you. So Macromedia, just say ColdFusion. I mean, it's important, okay? ColdFusion. Because this where stuff came from. There are still places in the world that actually run ColdFusion's middleware. You would know because your link will end with .cfml, okay? So when you have, and then Adobe, by the way, bought all of like Macromedia and the Flash. It's not Adobe ColdFusion, it's actually Macromedia ColdFusion. Okay, so then all of this is how you program it. Okay, there's like all kinds of things that ColdFusion can do. Just simply, if you have time, look at it, just for fun. Okay, and then there's an IDE for that panel. Many of these things that I tell you are fascinating. They're cool. They plug in some holes in the history of what you think of all this. They might not be like everyday useful. Meaning, most of the world does not run CFML anymore. But occasionally, you might come across a CFML page, and maybe you even come across a CFML server. Then what do you do? Okay, select this functions, and you can actually see the real programming functions. What the hell? 20. Okay. So you can do HTTP calls. You know how I said that middleware can communicate with other servers? How would it do that? You need some kind of HTTP object. That is so cool, right? So what this is almost like if you're in 571 in my class right now, you're running a Flask backend on Microsoft. That's exactly the equivalent of this. So your front end wants some data, but the data is now all that is being sent to ColdFusion, and then it translates your data into a different HTTP request, and then gets the data back, and then sends it back to you. That's exactly what this is. So from ColdFusion, from the middleware server, you can make an HTTP request like this. And this looks exactly like what the server wants. URL, username, password, what. You can even put some, just like post data or something. It doesn't matter. And then that connection would be made, and you will hopefully get some results back. So middleware can do like lots of neat things. Okay, that's what this was. You can program it in a few different languages. I showed you ActionScript, which is like Flash language. And then this is the template part, meaning everything that is going to be returned is usually already a pre-formatted HTML page. But then pieces of the page are not there yet. Then the CF app's job is to fill the data. And then you can do fault tolerance and things like that, meaning suppose a server fails, there's a backup for it, and you can do some load balancing. You can do like a lot of neat things. But the main thing is it can do database access, just like your Perl CGI program could. But now it's a more robust way of doing it. So in the end, you can see they're all doing the same thing, but in different ways. So what are some commercial companies that sell this kind of middleware? This is what I just now showed you some examples, okay? It's also called JRAM. This made by IBM WebSphere. It's a pretty amazing little thing there. And then JBoss is what I told you. It's made in, it's written in Java. There's also other things. There are things that are written in Python as well. There are Python application servers. WebLogic is one of the most famous of all of them. So the link for that. What is WebLogic? And just go read on this. And tell you it's a separate platform. And then it will sit between the web server and a database on this. Okay. Then it can log on to all kinds of services, and mostly log on to databases. There's so much in here about it. Okay. And then like this. So the front end would actually go in between is actually the server, the web server here somewhere. And the server would then send stuff to the WebLogic stuff. And then WebLogic will then make all these connections and then send data back. Okay, very cool. Just more and more of the same. Okay. In the end, back end is being translated to front end. It's a little like your Flask application in 5.7.1. That's what you're doing in the back end. You're calling TMDB, and they send you some JSON data. You can send it back to the front end. Over and over, the idea is the same. Okay, you want data to be presented, meaning this column of numbers. I want like a nice bar graph so I can visually understand it. So I need to format it. So once you understand the basics, it's like pretty neat. Nginx is a little bit different. Nginx could perform as a middleware, definitely no doubt at all. But it can also be its own web server, okay? It can actually compete with Apache or IIS for sure.
Yeah, I just want to add something. It says usually Nginx is used as a standalone web server, and it actually opens an HTTP or fast CGI, which is actually a socket connection to the middleware server. So the middleware server doesn't run within Nginx, but rather runs as an independent process and communicates through IPC. On the other hand, Apache and Microsoft's IIS actually loads the middleware DLL into the server process itself.
Very interesting.
So that's the difference.
Way, okay. This one keeps it a little bit separate. Maybe it's more secure then, right? Because then if the server process goes down, then at least it will be independently functioning. Is that right?
Yeah. So the real problem is that now, if there's a bug or vulnerability within the middleware, it only affects the middleware or server itself,
because it's isolated.
not the entire Nginx stuff.
Yes. So it's the opposite of what I said. So if the middleware fails, then if you don't do this, then the web server will itself fail. But then here the web server can keep running. Cool. Thank you for that. Yeah, then the whole ColdFusion stuff, right? I told you, they have these fake tags, okay, which is actually very interesting. So it looks like HTML, but it's not HTML. But after the ColdFusion middleware finishes running, this will all become like real HTML, okay? So it's a way of templating. It's all ultimately templating. You put in like all kinds of things that are, tags, ultimately they're tags. And all those tags get filled. So there's a whole language to fill those tags. Okay. So when you get some dynamic data, there's one way to do it. ColdFusion. So, and then this notion of web services, I think something go on to. Yeah. So the simplest web server, okay, the service is like that. Just whether you just send the question mark zip code equal to, and they'll actually tell you like that. Forecast. In the end, the thing that you're saying here would become when the client sends it to the server then sees this. They see a get request and then what do you want? And then the server can send a response back. There are so many of them. There's actually a random one. I don't know if I can bring it up now. If not, it's okay. I forget the exact link, but it's this one actually. If you go to api.publicapis.org and then say /random, then some random API is being called. This one is actually something called API slash. But every time you refresh the page, something else is being sent to you. So, these so-called APIs have become quite common. And all it is you're logging on to some God knows where server. I can go find out here. And then getting some response back from the server as JSON. Weird. Okay. So services, that's what services are. And then the user just gets it. Here I get raw, JSON, but I wouldn't normally do this. I'd have some nice UI for it. Then I can format all this. Okay, so I think we covered like a lot of cool ground, hopefully, about data and web service connecting. Okay, so then what all this means is this: a web server is a web server is a web server. Its job is not to serve you data. Therefore, we need some mechanism for the web server. Why even talk about the web server? Because the 8 billion people in the world don't have actual database accounts directly, but they can download any app to view them, and then they're going to tap on the app. And then they expect data to come back to them. And that's what it is. I'm looking up, California Pizza Kitchen's menu. So how am I able to see the menu on the phone? You have to do all of this. So in the past, there was no web, but there was still the vendors. So it all started with native access, Microsoft's whole bunch of APIs that eventually became 8.0.net. And then meanwhile, the web came along. The web said, what do we do? Then the CGI and the middleware, all that came along. I'm just going to go through this, show you what happened. It's all still Microsoft's world. Then Java gave you Java-based access. Then you had still JDBC, and now the database stuff comes in this way out. It's more interesting. Then you have to one way or the other do it. You can run CGI scripts. You can run, this can be done in many ways. You can run CGI scripts like this, or you can run APIs such as ASP or JSP, or you can have things like web application servers with ColdFusion markup language, any of the above, but they're all dynamically data generating. Okay, so that's good. Is it good to iterate, manipulate, simplify data on? Okay, that's a great question. I love it. because it's basically 6 of one and a half dozen of the other. It entirely depends, Yash, that's all it is. The clients can easily handle it. We can do some neat things right here. But more and more, right, the servers are pretty powerful, their own cloud. So maybe the client just expects, give me as little as to do as possible, like YouTube was to the work. But it's simply a division that the application programmer decides. When you write the front end and the back end, the team decides what should the front end do, what should the back end do. In general, it's nice for the front end to do as little as possible, because not everybody has powerful phones with lots of RAM. You want to do as little as possible. But that puts the load on the server. So yeah, just one over there.
Yeah, there's something called, I think, a model view controller.
Right.
And you basically want your data to be processed, I think, is in the model and controller layers. The view layer is just for presenting whatever we have.
Correct. So then what happens is in that, so okay, that is correct. Then what is like this? When I actually get this data, then I'm getting the data directly. Okay, so then the server is not doing this rendering. But then the view that I have, this SVG view, is really what's doing the rendering. So in that sense, it is true that the server just sends you raw data. But then the opposite of what I said is the server would then send me this image blob, like all this code that I'm running, right? Say the server ran all this code. It's going to generate the same image that I generate. And I will get a blob back, okay? Then the response would not be to actually do all of this. So here the response is I'm doing all the processing, but my processing would be very simple. Turn the blob into an image source, and then set some kind of an image, I make a little image element, and I just instantly just get it. So then my browser doesn't do any of the work at all. So yeah, the server can send you raw model, and you can do the view yourself. The advantage there is the controller, which is the UI. I can have a little UI. Maybe I can spin the teapot. It's all happening here. That might be the advantage of just getting the model, the raw model. On the other hand, if I don't care about that, I just want to know what the teapot looks like, then the server can render it. In Amazon, by the way, there are so many products that you buy that are actually rendered in CG. Say you buy like a nice, coffee pot or something, or some air fryer. You might think it's a photograph, but increasingly there are 3D models that are stored that generate beautiful images for you. Even when you spin it, actually spinning it, the server is actually doing the rendering, then pretending the boundary is spinning. So the server actually does a lot these days. But you always have the option, like I did, of doing the client. Okay. Any more questions on that? The part that I have here that I wanted to iterate through, not every line, was up here. I can find it really fast. Okay. So you see the 896 polygons, okay? So if I go through every 100 of them, maybe I should do it. So that many polygons. Now I can print the data. Just to show you that I'm getting raw data, it's actually up here. You can print the data just to show it to you. Up here. It's going to show up here. So this data is actually what the server sent from bottom up there. Here's some data, like 96 triangles is what it sent roughly. And then I'm now rendering it. So you can do a little bit of both. In this case, we got the data and we're rendering it. Or you can tell the server to do it all. This entire too. All right. So let's now completely switch gears and talk about indexing, okay? And we'll just keep going. I'll go till about 7:40, then we can take a little break as usual. Then we'll do some Q&A. I don't want to keep talking the whole time, how you guys a little bit. But this was fun, right? Because those are the two big worlds. It's all about data, it's all about web. And so now you know how they are combined in the world. It's completely run on this. Oh wait, actually one more thing I want to tell you. Yes, so along those lines, just before we leave the topic, it's actually massively fun. You go here. It's actually a math application server. Okay, that's such a weird thing, a math application server. What does it even mean? It's not serving you math equations, okay, although you can definitely do that. It's not doing that. Instead, it's run by the American Mathematical Society. What they want to do is, suppose you are a math scholar, meaning you want to go to the Courant, Mathematical Institute and do a PhD in math or something. You have a math application that you would submit. Likewise, say you're a faculty that you are trying to write a recommendation letter for, then that's what you want to do. So this site wants to integrate like all these people. You can get an account of one of few different types. You can be a student, or you can be somebody who nominates a student, or you can be somebody who writes a reference, or you can be the one at Courant Institute who says, should I pick the student or not? So many different kinds of people, okay? And the idea is, what kind of data can you store about all of them? Meaning, what does the student want to do? That's what the student wants to do. The student wants to, log in, search, all this, right? So what is happening here is all just fake data, by the way. But it's funny though, because it is pretending it's all this database, okay? It's getting all this from a database. And what will come up? Did you see? Oops, okay. So all these fields will eventually go fill a database, is my point. So we made a whole backend database. Also something. They like this. I don't want to upload. I don't want to be a student. Okay, I'll be a reference library. Okay. So everyone has like data that this server stores. Let's do kitten and cat. Okay, so kitten is going to log in, then submit this better. Yeah, then imagine this all real data. Okay, then this is what it looks like. So I have a reference letter that I'm writing, and then it's gonna, just ask for all these things will all then go back on the server. They're helping people do like a whole application system. But then my point here is that it's all being accessed to the web server. These are all the backend communication. You send extra data to your server to all the question mark things, and then that's what it's going to use to point to a database, like some private ID or something. Really, really cool. Like that number is also used somewhere. In fact, if you say submit, wow, that made a separate request. That could be here. The question mark ID equal to the two times. But it's neat. Oh, okay. Again, it says what are the applications available. There's so many different things. Yeah. Okay. Once again, these are all the database columns. Okay. So for every kind of school that offers you scholarships, what is the ID? What's the title? What's the whatever? All this database stuff. Classic relational database, it seems to me. Okay. Finally, how can you make things go fast? Make things go fast by so-called performance tuning. Ooh, machine learning. Here. Let's type out. Okay. So I'll not rush through all that thing. I'll do what I can. And this is also a very useful topic as well, because we want to make things go fast. So what are the tips and tricks there? Chapter 11 in your previous 11th edition of the book. 11 means 11th edition. By the way, this is so cool if you never noticed. It's raining bits on people. The whole world is 1 0. So what does tuning mean? Tuning means eventually one single word. That's what tuning means, as fast as possible. It doesn't matter how you do it. You can have fast hardware. You can pay for extra bandwidth so you can serve more people. You can have a much bigger disk space so you don't do paging. You can do any number of things. You can write good SQL. You can make your server be like highly efficient in terms of its linked list, memory access, all the above. So do anything that you need to do to make it go fast. That's all it is. So it's a bunch of activities and procedures that reduce response time. Same thing. So how long is the client waiting? Tap, 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 tap. Oh my God, look, 5 seconds. It's spinning. Screw it. I don't want, a flash drive from you. I'll order it from somebody else. So the business literally loses money. The response time goes up. So they'll do anything that they can to keep this as small as possible. Respond instantly. You fine tune it like a car. How do you make it run at optimal speed? Okay. It's all about just maintenance and good practices. Minimize bottleneck. Just general things. But the main idea would be you can do it in two very radically different ways. This has almost nothing to do with each other. One set of good practices, a different set of good practices. This one is by the SQL programmer. This one is by the backend. These days it is a cloud backend. So these days the data engineer's job is to actually maintain these kinds of servers. So I'll call it the backend people's job. This is the front end. Front end does not mean UI front end, more like application front end. Okay. So in other words, good SQL, good tuning. We'll do this first and then we'll do it. Okay. So then this diagram that we never brought up before is really how it's like a prototypical diagram we all use to say how does all this work. In other words, what does the relational database access mean anyway? So let's spend a few minutes on this and it'll make everything pretty clear. The so-called DBMS, the database management system, is a whole collection of processes. I can just loosely say Unix processes. It's a bunch of processes. And when we talked about locks being granted revoked, a list of all the locks that have been granted transactions, that is the lock manager. And then just tell you a few of them. The user process is the one that knows your credentials. So I submit some SQL to look up the USC president's salary. You should come back and tell me, even though you know the table somehow, you know the column name, you don't have access to it. Well, no, run the query for you. It's all that. And then, so scheduler is the one, they both work together. So these are the ones that sequence transactions, okay? So what transaction, like runs after what, how can you interleave them? And then optimizing. So optimizing, first of all, let me tell you about the listener. Listener is more like a front-end compiler. You write bad SQL, you leave out like table names and some extra comma, forgot the semicolon. It'll say bad syntax. You probably get this in Oracle all the time. That is the listener. So it won't even go any further. It just says your SQL is bad. I don't know what you mean. That's pretty easy, okay? It's simply a listener. But if you get past the listener, the main job of running your SQL query is actually like these three. The optimizer is the one we'll focus on now because that is the one that can do performance tuning. So what the optimizer does is it can look at your SQL query, what query you want, and possibly rewrite parts of the query, possibly combine parts of the query, or possibly use what is called indexing. So I'll tell you about indexing to make your query be optimized. It's all about optimized execution. That's the notion of optimizing. So the optimizer is a very important part of like all of this. Okay. Okay. So when the optimizer finishes optimizing, that's what it does. It runs an optimized version of your query. But before I tell you any more, this is supposed to be a very small, like a low bandwidth, so to speak, link. It's a very tight link, meaning we don't want to do this too much at all because it'll completely slow everybody down. That is where the optimizing comes in. So how most efficiently can I use it? Like how little access do I need of an HTML my queries? It's called an IO bottleneck because this is where the actual data lies. It's where all your entities, tables, constraints, metadata, indexes, all look here. Okay, so you want to do this as efficiently as possible. Okay, once the optimizer optimizes what to do, it gets data in the most optimum way possible and stores it here. Because your actual SQL query is going to execute here, not going to execute here. Just serves data, and then it's done. Then it'll serve somebody else's data. So your data copy goes here. And you can do all your, select from, where, which, having what, all of that, right? You can even do calculations here. You can update your table and put it back. So lots of calculations are happening here. This is the copy of the table that I always talk about, okay? There's a copy. There's not just a data copy, and eventually things will go back to you. Those will go back to you. There's also a SQL cache. This is almost like a key to a compiled version of SQL. So the SQL that you write is more like not compiled, like high-level C++. The compiled SQL is more like assembly SQL. It's called the access plan. In the access plan, you will not see any SQL statements at all. There's no select where, having, group by what, there's nothing. It looks like table names, row IDs, column names, and so on. Unix disk drive names because it knows about all that. So it looks like a pretty low end, just get this row, get that row, after you add it, put it back. Simply IO operations, okay, like a register operations almost in a CPU. That's what's so cool. So once it optimizes and knows to run your query really fast, it also caches the query. It caches the access plan actually, the compiled version, and also caches the source code. So the idea would be you run the exact same query tomorrow morning. It does not have to optimize or do anything. It'll compare to see if the query already exists exactly the way you did it before or not. And if the answer is yes, well, the compiler, this is like a SQL compiler. It compiles it. It turns it into an access plan, okay? Okay, so if the exact same query you keep asking every single day, who got between 3.9 and 4.9, or how many CS students signed up today? Supposing registration is going on, right? Or fall in your term is starting, the registrar always wonders, how many students are in a certain class. You run the same query over and over and over again. And maybe the cache can just say, hey, I already have the query optimized. Then you just run it directly. Only when the query is new, then you delete what you had in the cache and you update your query. Okay, so this is the way of like not doing optimization over and over again. That's what this called is. There's some pretty neat things that are going on here. Okay, but overall, the idea would be your query comes in, and then these three would make, especially this one. This is all already done. The query is running. The optimizer will then compile your query, turn it into an access plan, and get your data, and do the results, send back to you. Meanwhile, also put that in the cache if it is the first time it's seeing it. And this repeats over and over again. So this is basically what the server does, and then we can optimize it. I'll even tell you that, and then things can go faster. When you optimize like how the server actually gets your data, that's when things like indexes come in, or how long is the table, or how many rows you have. The optimizer can decide some very good ways to access the data. You can even gather statistics on how the whole DBMS is running, and use the statistics to decide what path to take. Meaning there are multiple paths of getting the same data. For example, you can get data one row at a time, or you can get them like 1 megabyte at a time. So there's lots of different ways in which you can get data, and the optimizer decides at runtime what to do. Maybe our DB can query the tables to update data. Right. It's not even about the traffic. It's more like exactly what SQL query is coming in. It's more about the query because the same query does not have to be, re-optimized because you'll probably get the exact same access point. It's about just simply looking up that. Okay. But yes, it happens, yeah. Because even when there's less traffic, what if the query changes, then this one more time? It's because this data is not like HTML data, where you have an article you're selling. The backend might change, So there's also that to consider. So I wouldn't base it really on time. I would base it more on what query actually came in. Say I want like 3.9 and above students. It's still the same query, even though I have more students or less students in 3.9 GPA. But how do I run the query? That is exactly what is key. Okay. So that picture actually explained a lot, which means, all right, so all the ultimate data in your entities are all called data files, meaning one entity can be in more than one data file. Exactly, we're cache. That's exactly right. You're caching the SQL query, correct. This data that is cached is thrown away. This data that is cached, this data is thrown away because then somebody else's, data can go there. This is what you're caching. Yes, that. Sorry, I didn't. Uh, so data files, can hold like more than one table, or a table can be in more than one data file. And then when a data file fills up, more and more students are signing up there first. They extend the whole data file by one more block. This is the classic programming, okay, in C++. You would not want to allocate like 1 byte at a time, okay, that's highly inefficient. So when something fills up, allocate a whole bunch of bytes, and then fill it all up, then allocate a whole bunch of bytes again. That extending is called an extend, like a noun. Like an extend can be, I don't know, 32 megabyte blocks, for instance. That way you don't do it over and over again. And then this all set your configuration files. Literally extending your table space, so you can add more rows to data. And then your data files are grouped. These data files are grouped in file groups. They're also called table spaces. All that this means is if certain tables are constantly used together, for example, checking accounts and savings accounts in a bank, they should be kept together, as opposed to a loan mortgage, table that is like over here. Okay, because usually people don't go from checking to mortgage, or savings mortgage. Like things that are used together are kept together. That way they can be accessed more efficiently. That's what this is. Then it's called a table space of files. Okay, very simple. And then data cache or buffer cache. So this is the one that I gave you the picture. This is where the queries actually execute, like over here. Once you fetch the data, you put it here and you run it. Because that way then you don't have to use up memory. All this is there. And this is what Yash was asking. A SQL cache is your actual query cache. For the same query, you don't have to re-optimize. You can just simply serve the access point from the SQL cache. It's also called the procedure cache. Stores the most recent executed statements. By statements, we mean the backend, meaning the compile statements. That way, the same query can just simply be looked up and the compile statements can be returned. What this is all saying is, I have a source code in C++ and I compile that to exe. Then next time I want to compile something, I won't even compile. I'll compare the source code with the previous source code. If you give me the same source code, I'll say, look, the exe already exists, just to use it. That's what it is. Yeah. And how do you compare like lots of big SQL queries with other big SQL queries? You don't actually store the query itself. You store like a digest. You actually hatch it and you store a signature for it. Then when a new SQL query comes in, create the signature and just compare the signatures and see if they match. And if they match, then return the point. Otherwise, exactly. That's exactly right. Now, the compilation time includes a lot of optimization, so that could be a pretty involved step you're saving your power. Correct. When I was in middle school, did you MemSQL? Yeah, definitely. MemSQL is actually very interesting. Sure. Huh. In fact, I think you are the one that actually brought up Redis. So MemSQL is very simple. It holds pretty simple key value pairs. You're right. You can poke any key and any value. CPI is that simple. If you give it a key, it will return the value. That's it. I'll definitely talk about MemSQL, okay? In the NoSQL part of the course. All right, so then the whole point is that, SQL cache is useful because you don't have to re-optimize over and over. And then data cache, again, is because, the raw data files in the back, they're not accessed frequently. They're probably not as fast as RAM, but you can store your data cache in. You cache the program and cache data. And that's it. So this is the key, okay? You want to basically hit that little wire as little as possible, meaning you don't want to keep pinging. Like, it should not be too many requests. The optimizer will gather up as much as possible and do it as little as possible. But again, remember, millions of people on Amazon are doing the same thing. Cool. I'm going to click on it, see what I can do on it. Thank you. All right. Then my history would remember it. So no need for this. Moving on, it's 7:32. Good. Yeah, I just not talked about this. And then talked about this as well. Okay, so these are the processes. I told you there were a few blue color little boxes. The listener is the one that is going to actually listen to your SQL request. And then if the requests, have no syntax errors and pretty simple, passes basic checks, then it will go on to other things like the optimizer. I see. Indeed. Okay. User. So who is the user? That's you and me making the queries. So we need authentication. Okay. You have a user process. And the process knows what tables are allowed. And so then the database maintains process for you. Like Amazon has all your client accounts. A scheduler is I told you it's about concurrent. So this is the transaction management part of it. Scheduler. Not relevant right now. The scheduler still works. It's also not relevant. You already got the locks. Your SQL is executing. So we shouldn't worry about all this. Sure. So the main thing is optimizer. Okay, thank you. The optimizer is the main thing we care about. Okay. How do you actually take the query the user wrote and then get back full responses for them? So this notion of the optimizer process, what does it do? The way it works is it's called a mode. You have a mode that you can set. Like this is the mode, that mode, whatever mode. So the modes can be classified. Okay. So one way you can classify those modes is based on the selection of optimal order. So you look through your query and say, what are all the tables that you want? And reorganize the way the tables can be accessed. Like blocks of nearby tables that one access. Then you can get the data as fast as possible. Or look at your query and group it based on what sites your data reside in. And then group based on the sites. Make for a whole bunch of sites, just one request, so we can also your data. It's doing like also tokens of tokens behind your back. The programmer has the SQL writer. There's no clue about all of this. These are the main ways in which you can classify those modes, okay? Meaning you can set this in the configuration files and study it or how it works, like what works best. One is called based on operation. One is called based on timing. The third one is called based on information. So I'm going to walk through what all this means. And then I think we can stop for today. All right. So the first one was this operation mode right here. This operation mode, what does it mean? There are two kinds of operation modes. One is called automatic mode, one is called manual mode. It almost looks like a camera, like a DSLR camera, or maybe a car. It's an automatic drive and there's manual stick shift. The automatic query optimization is you don't have to do anything. You set the automatic mode, and then the optimizer will automatically do the right thing. That's called that. On the other hand, manual query optimization mode means you need to know so much about how the data is actually accessed because you have to set some parameters. If you're highly specialized, you know how it all works. You go in manual mode. Like again, in a camera, if you know exactly how the shutter works and you know how the lens works and everything inside, how the exposure, timing, all of that, you want to do it all yourself. But most people in the world would say, where do I click? Just tell me what button should I push. So then that is the neat part about it. They both have advantages. Okay, timing. So again, the second way to classify these modes is based on what's called timing. What does timing mean? This is what timing means. So timing means static versus dynamic. This means when the whole query starts to run, your query is your SQL command got multiple tables, lots of reads, lots of writes. All of those reads and writes will just kick off, and once the reads and writes start, there's no more optimizing. It's called static, like compile time optimization almost. So whatever the optimizer thought during compile time should happen, will happen throughout the entire query for all the reads and writes. That's one way to do it. The other way to do it is while the tables are being accessed, the optimizer is watching it and potentially changing the way the rest of the tables are accessed. So it's dynamically changing how the whole access works. That is called dynamic query optimization. Obviously, a lot more overhead, okay? Where the optimizer is constantly watching what is happening. But maybe you can get much, much better responses from that. Just like Google Maps in a way. Before you leave home, you look at the traffic map and it says, oh, I'll take the freeway. It's more like Waze. So with Waze, Waze is sitting on your passenger seat you're driving. Halfway to USC, there's an accident in the middle. Okay, in 500 feet, take an exit. So this at runtime telling you what to do. It's more like, initially I pick some pattern, I'll stick to it. That is static versus dynamic. Interesting, right? So they're both useful, obviously. Yeah, sure, man, that's very smart. I actually asked the question. Yeah. Hold on to the thought. I'll ask the question. You already know the answer, but I'll ask it in a different way. You might not recognize what I'm asking. But loosely speaking, yes. It's a good analogy right there. Okay, moving on. There's a third way in which you can classify the modes, right? The third way was based on this notion of type of information. Like, what does it even mean? Just again, a couple of different things. This is also related to your question, Yash. Type of information is statistically based versus rule-based. Wow. What does that even mean? This means the optimizer process, can pretty much poll, meaning measure times, access times for tables. Like how long did 100 rows take? How many milliseconds did it take to load like 100 rows of data? What about 200 rows of data? It is gathering statistics, okay? Or what about tables on this server versus another? What table? So how does all this differ? You can collect all kinds of data. Then you can do more optimization based on the data. That is called statistics collection. There's actually a SQL command for it. So anytime the DBA can even run the SQL command, the statistics would get collected and go live somewhere as data, and the optimizer can use it. Or the optimizer can run that statistics command anytime it wants. So that is the whole mode of working, is you poll like what is happening while the thing is running. That's one way. Dynamic is automatic, so then you don't have to do anything. Manual is what I told you. You have to run the statistics generation command, and then the optimizer can use it. So there's a little division here, okay? On the other hand, rule-based is entirely different. No statistics at all. So experts come in that have seen this kind of data access for many years. They come up with some costs for accessing these tables. Those costs are hard-coded. It's all in their heads, and they're called rules. And those rules are then used to determine access. A very different way of working, okay? But those are two different ways. Therefore, here there are two different ways. Here are also two different ways. Here are also two different ways. They're all like 2 to 2, okay? Except within this 2, this also breaks into 2. That's what I mean, right? And one of them, 2 different ways. The other one also, 2 different ways. The third one, also 2 different ways, but now you have to know. Cool. Okay. I'm wearing a big hat, everybody. This is so cool. Look at me, look at me. Yeah. Okay. So, okay. Move on. Yeah. 740. Perfect. So I think we should stop, okay? So what I told you was this notion of optimizing. Okay, so optimizing can run in these 3 different modes, and then you pick which mode you want. And within each of those modes, there's 2 different kinds. So ultimately, you pick like one of them. Like say you pick that, and then you watch how the whole access works and how good things are. If you don't like it, you change it to one of these, or you can do the timing change between static versus dynamic. So in the end, you experiment, then you pick the good configuration for your system. And then you have to probably modify it every few months or every few years because data access patterns change. So it's not like forever. Even the brute force solution can be optimized. Possibly, yeah, exactly. Yeah, brute force can be optimized, meaning you initially do brute force and you discover the full solution and then you can optimize it. Yes. So why don't we take like a 10-minute break and come back at 7:51, okay? I can do all this another time, no big deal. I mean, no hurry at all to finish. So let's be back in 10 minutes, you guys. Wait. Cool. Hey, cool. Okay, we're back. So I'll come back here and here. Put up the chat. Neat things go on in chat, you know. But check this out. So what I did was just go through my directory again, just carefully, and it was right there. Probably just scroll right past it because I was a little weirded out that the ODBC driver was missing. That's not possible. See, here it is, okay? ODBC, there's a whole bunch of them, but they're all ultimately related. It's one big ODBC. So this is exactly what makes any kind of database access possible on my machine. Not that it happens, but it could be possible that anything over here, even my browser could be actually storing cached data or maybe even cookie data on my machine. And I have all these research databases, right? This is called Zotero. So this keeps track of all my bibliography. So then all the entries, that is a relational database. Maybe they're actually using ODBC to store stuff in there. So any number of things can go on. But the neat thing is that single file is what makes it all possible. So if that is corrupted or you delete that, the things just have to really stop working. It's a little dangerous right there. Okay, I just had to find it. Pass it on to you. Okay, so let's do some Q&A. Okay, I want to go back to last time and ask you just a couple of fun questions. One is actually very useful. it has to do with the notion of locking and when locks can be released. So I asked you something about conservative locking versus strict locking. So the question really is, what does strict mean, or why do you need it? Okay, so let me remind you of what all that was. So I can go back here and go to week number 6 and click on it. Okay, so closure, all that's pretty simple, right? Closure is good, and we cannot make it all serial. Things are very slow. This part, all right. So the locking that we presented in our class in the lecture was called static, or sometimes called conservative two-phase locking, where you have this one phase where you simply build up all the locks, and during that phase, absolutely nothing else can happen. And then after all the locks are acquired, and only after all the locks are acquired, the actual transaction can proceed. That means there's a guarantee that there's no deadlock, because by definition, you have all the locks that you would ever need, and so no need to ask for locks, for more. You already have it. Okay, so just for protocol, we'll just draw that again, okay? So in what is called conservative two-phase locking, this time, so time goes this way. So until all this time, you acquired like all the locks. So at that point in time, you have all the locks that you need. And the actual reads and writes are all happening here. Many tables, as many cells as you need, whatever. And finally, your whole transaction is done. And when the transaction is done, you can start to, when I say transaction is done, listen carefully, okay? It means I'm done with all my calculations. That's what it means. So I'm still committing, I'm still possibly even aborting. But at that point, I start to release all my locks. So when I come to that point, all the locks are gone. It's called conservative. As opposed to a different scheme, in fact, two more variations, where something called a strict 2PL. In a strict 2PL, what will happen is, there's a variation on when locks are released. This locking release that happens only happens for read locks. Read locks can be released. But on the other hand, a little bit more time, you would hold on to all your write locks. A little bit more time, hold off your write locks. And then pretty much release all of them at the same time, meaning just a finite amount of time. But you wouldn't do it like that at all. You would keep the write locks for a little bit longer time in the next version. So why do we do that? Why hold on to the write locks in this version? In this version, what is the reason to keep write locks and then release them all pretty much at the same time?
I'm thinking about like minimizing the amount of write conflicts.
When would you get a conflict? You're on the right track, but how would you answer it? Yeah.
If I have two applications that are trying to modify the same value at the same time, if I use conservative locking, then I might get a phantom write. I don't know if that's the right term, but basically one thread thinks that it has written something only until later it turns out that it had failed. But in SS2PL, the application will immediately know that it can't write and will just spin. So I'm assuming that it makes the logic of failure process simpler because you don't have to think about the condition where you think you might be able to write, but it turns out you can't, and which could make the application logic more complex.
Interesting. Are you talking about this transaction or some other transaction?
I said if there's another thread.
When you say another thread, you mean another transaction?
Yeah, another transaction that attempts to write. In conservative writing, it might think that it will be able to write, only to fail later, which would make the application logic that actually deals with these transactions more complex.
But what would be the difference between this and this, though, from the write locks point of view, okay? So in other words, the answer more is focused on what happens here. But just to answer your question, supposing the write locks are released one at a time, okay?
Okay.
You still are able to get them. And if you're able to get them, then you can read and write. So that probably wouldn't be introduce you. It's actually related to what happens here. So the main thing that I talked about was commit versus abort, okay? So what happens when the application commits? Or even more importantly, what happens when the application aborts? Is the question, okay?
When the application aborts, it has to roll back everything that has already been written, which will take time.
Yes.
But if some other application is based on a partially written result, then it could be screwed up.
Exactly. Yeah, so that is the good answer. Okay, so the answer is that if you screwed up in this transaction, it takes you this much amount of time to actually commit. Commit is a good thing. Commit means you don't have to go back and fix anything. But suppose you want to abort, then these write logs that you had, the things that you wrote, you probably have to modify the value that you wrote, put back the value that was previously there because you're completely cleaning up yourself. Suppose you didn't do that. Suppose you did not hold on till you actually abort. Before you abort, if you release the lock, what will happen is some other process would come and write some value in that cell, but because of your aborting, you would come and overwrite the value. That process would lose what they wrote, okay? They're like overwriting. So in other words, that's this notion of cascaded abort. So when you cascade aborts, when you abort, sadly, because of what just happened, you have to then abort the other process as well. So the abort would cascade if you release locks one at a time. Because they got the lock thinking you are not going to abort, but you decide to abort. In this situation, you hold all the right locks and then release them afterwards. After you either commit or you abort, doesn't matter. Then you can avoid the whole cascaded aborting, okay? In other words, if you want to abort, it's all just your problem. Nobody else got the right lock. That is the reason for doing that. Now my next question is this. Okay, so that's that. It makes a lot of sense. This looks weird. It's called rigorous. It's called stricter, strong fit. There's access to many names, okay? Here you do one more thing. You hold on to release locks as well. Wow. You don't even release the release locks. You hold on to every lock that you ever have. Release shared lock and exclusive release and read and write. And release them all at the same time. The big question is why? Yeah, correct. So the answer, so yeah, there was a question that came in. Do you release the write lock after you're done committing? Yeah, in the previous example, like in this version, yes. Not only after you're done committing, even after you're possibly done aborting. Because either way, you still have all the right locks. You can do whatever you want with it, okay? Nobody else will be affected. But yes, the short answer is yes. But this looks like a little strange to hold on to read locks. There's possibly no reason to hold on to read locks because you're not going to screw up anything. But why do we do it though? So there can be infinite loops. If one aborted, it will try to abort ongoing. The not more like a cascade. So what you're talking about what's called cascade. The aborts can all affect each other. That is the answer to this. So yeah, the cascaded abort is what you want to avoid. That is why you hold on to all your write locks and release them all at the same time. But there's really no harm in releasing read locks at all. It doesn't matter whether you commit or abort because you only read all these values. But most database implementations in the world, believe it or not, hold on to read locks as well. So practically every relational database does not do this, does not do this. They actually do it. The simple question is why? You stop what you're asking by holding on to all the right locks. So to answer Yash's question, if you keep all the right locks till you decide you absolutely don't need them anymore, that's how you can avoid cascading. So that is the middle part. That's what this was. In this one, you hold on to all your write locks, but not read locks because you don't have to hold your read locks. But in reality, all implementations, you look at the source code, it turns out that they're also keeping read locks. It seems like wasteful. So my simple one-word question is, can you think of why? This where some creative thinking comes in. It is not a technical answer at all, meaning you don't have to do it.
Okay, let's assume that there is another transaction that relies on some value that has been written in the current transaction.
Mm-hmm.
And when you are aborting the current transaction,
Mm-hmm.
if you hold the read lock, then the other transaction will be blocked. But if you don't hold the read block, the other transaction will read whatever you've written.
Mm-hmm.
And if at this time you decide to abort, then the other transaction also needs to be aborted because you are rolling back the values you've written, which the other transaction relied on.
Yeah, but when you read values, though, you're not changing the values. See, that's the thing. In a read situation, right, it doesn't matter if you abort or commit. You got the read lock because you're only trying to read the value. So it wouldn't actually matter at all. Think about it, okay? So say I have a table here, okay? I got a read lock to read that table. The cell had value 8 in it. So it doesn't matter if I keep that read all the way for myself and release it, or if I release it here, somebody can get it.
I'm thinking if you're writing a bunch of stuff and you don't hold the read lock, then say if I write a cell to 8, which was previously 6, and then another transaction reads my newly written cell and it reads 8, and my transaction starts to abort, which means I have to roll it back to 6, but the other transactions actually relied on the 8 that I read.
A good point. Exactly.
Which it also needs to be aborted.
Yeah.
That's what I was trying to say. So the easier way is just if I hold the read lock, I block out the transaction. This won't happen.
Yes, no, that's very smart. Exactly. So what he's saying is, even though for us it was a read, if you release it, it's going to become a write for somebody else, and then that somebody else is going to put some value in it. And then when you abort, you put your whole table back the way it was, and then you're overwriting the chain. That's a very good answer. Okay, it's a great answer. There's also a simpler answer, by the way. That is definitely what you can avoid. The simpler answer is this, believe it or not. In this situation, when you hold only write locks, it's more work to actually track what is a write lock and what is a read lock. Instead, it is much easier to hold on to all of them at the same time. Okay, it's simply an implementation detail. You don't have to check the lock type when you release it. Just hold on to all of them. Simple answer. But yes, it will also avoid the whole thing that you brought up. Okay. In any case, just know that this is what all databases in the world do. Okay, okay, good. Let's move on. This is an interesting question because let me see who's going to guess it. Okay. Okay. So you have the Newton had a couple of cats. A big cat and a small cat. Big cat and a little cat. Then Newton calls his carpenter and then says, you know, I have a back door and I want you to make 2 holes for me in the back door. A big hole and a small hole. The carpenter said, why? Why, Mr. Newton? Why, Dr. Newton? Then Newton said, the big hole is for the big cat to go through in and out. The small hole is for the small cat to go in and out. Except the carpenter didn't do all this, right? They're just talking. And then the carpenter said, you know, we don't need 2 holes. Newton said, why not? Because a small cat can also go through the big hole. Newton said, that's not possible. And the carpenter said, really, why not? Well, because the big cat cannot go through the small hole, so the small cat cannot go through the big hole. That's basically what Newton said. And so then the carpenter had to prove it by just making 1 hole and saying, look, it works. So what is an example of what Newton tried to do? He was foolishly trying to insist something. What was he trying to do? There's a quote, there's a thing that a US philosopher made, and it has the word foolish, and then there's some other word that I'm trying to look for. And somehow this is related to your whole processing with single and multiple sites. So who can make the connection for me, okay? We talked about processing all happening in one site. Yeah, exactly, you go. And then all data being held in one site. We also talked about fully distributed processing, where we said all the data and all the processing can be distributed. And then there was a third case in those. So how would you link this whole Newton idea with that? Anybody? First of all, how many cases did we have then? With multiple and single. Single data, single processing, multiple data, multiple processing. How many cases did we have?
4?
No, we didn't have 4. Surprisingly, we did not. 4 would be the logical answer, but we didn't actually have 4. We had single processing, single data, like a mainframe. We had multiple processing, multiple data. And then we had single data, multiple processing. You send your stuff all over the place, it will land, like a file server. But what we did not have is single processing, multiple data. In other words, everybody in the world did not send all their stuff to your CPU and you didn't execute it, okay? So if you look in the notes, I put a little red X, okay? That's actually what this is. This is called consistency, okay? It's actually called foolish consistency. By the way, I didn't try to call you a fool. But that is called foolish consistency when you insist that just because there are 3 cases, symmetrically, there has to be a 4th case. Like I need to make an implementation where all the data would be sent to me. It's like practically useless, your server would crash, right? The case doesn't exist. Therefore, the moral of the lesson is, in the world, you should not always look for foolish consistency because sometimes it's actually foolish. So what US philosopher had a quote that said, foolish consistency is the something something. Foolish consistency is the what? Oh, anybody at all know? You can Google it, but try not to Google it. Foolish consistency is the something something of small minds.
Is it Hobbes?
Yes,
Hobbes?
it starts with Hob. You're absolutely right. Hob, Goblin.
Oh,
Yeah, Hobgoblin. Yes, that just means gotcha. Okay, it means it's a thing that will basically, kill you. Meaning the one that makes you look foolish. Yes, a foolish consistency. If somebody has it, then they basically have a small mind. This actually is Thoreau. Okay, so Thoreau is an amazing philosopher. I want to just Google his name, and then you can read the quote. So foolish consistency. Foolish. Wow. No way. It's crazy. More complete. Amazing. Oh wait. Duh. Okay. So Thoreau and Emerson. It's the other guy. I'm so sorry. Okay. Not Thoreau. I'll correct it. It's Ralph Waldo Emerson, R.W. Emerson. So it's not Thoreau, but Emerson said, foolish consistency is the hobgoblin. Little minds, small minds, little minds. Cool. And then there's the whole extra thing that goes on with it, okay? But that's the point of saying we shouldn't look for the fourth category just because other three categories make sense. This does not make sense. Still doesn't make sense. Okay, so then let's move on and do other things. That's like a weird tangent. Why would you want to replicate your data? Suppose your data lives on many servers in the world. What are three reasons to make extra copies of them? One reason would be
Availability.
yeah, sure. Specifically, what would you mean by that? Like, suppose you are in Japan, I'm in the US.
So if one goes down, then there's the other one to serve the customers.
Yeah. That would be more like a failure reason, okay? Although that is related to availability, obviously. But the word availability means a slightly different thing, exactly locality. So what if somebody in Japan is easily served through a Japanese server, right? That is also availability. So that is about throughput, like serving as many people as possible really fast. So then you would put data near where the people are, the content delivery networks, okay, CDNs. But what you said is also correct. If something goes down, then that's called a failover. You want to cross over to a different copy of the same query and continue running. Then the user notices a small little, a bit blip, but it still keeps working.
Another reason is load balancing. So basically, I could scalability. I can scale three. I can if I replicate three servers and all are actually been read queries, then I could like raise my read throughput 3 times.
Yeah. That's a different way of saying what I said, but maybe it could be different. Meaning, if the server knows, like what is the nearest CDN, it'll then forward your request. There's a proxy that receives all the calls. Then say you're in Japan again, then some server near you that has the Amazon Japanese catalog would actually serving you the data, would be serving the data. So it is load balancing by holding the data near where the customers are, especially when you have a global operation. But you did not bring up the main, like really horribly amazing, scary reason. None of you did so far. Although one of you brought it up, but didn't fully explain.
Say if there's an earthquake that hits Los Angeles,
Yes.
then the server in Japan probably will still be fine.
Yeah, backup, right? That's the biggest reason. You want to replicate, if nothing else, for backup reasons. Because if you only have one copy of something, it is gone. Oh my God, it's completely gone forever. So yeah, the simplest reason is backup. The second reason might be like, throughput, meaning load balancing. The third reason might be if one query fails in one server, you want to send the query to a different server so people don't wait too long. That happens only in failure, okay? Okay, so 3 different reasons. Now, okay, so replication is cool, but then what happens to consistency when you replicate? Like, what should we be careful about? It's a trade-off. You replicate too much, and what happens to consistency potentially?
Yeah, it's more like you have to be able to tolerate certain level of inconsistency between different nodes. Say, if I'm replicating with a server in Japan, and we're using like the undersea fibers that's between Japan and the United States,
Right.
And anything could happen with the undersea fibers. If the fiber goes down, then you are screwed.
Right. But then why do you talk about the fiber? Meaning there's something else that happens that you're not mentioning. Your answer is right, by the way. But then there's something else that we have in mind when the whole fiber comes into play. Like what happens on one machine, for example. Somebody wrote Yash.
So when you make a change in one
Yes.
node, then you have to do that for all the other nodes.
Exactly. So that's the point, okay? So if I update the catalog in Seattle and I put some book on sale for 10% off, then until that change is replicated in Japan, whoever orders the book in Japan will pay that extra money, the extra 10%. Obviously, Amazon being a nice company, Jeff Bezos does not want your 10 cents, okay? They'll refund it to you at some point. But until then, technically, there's eventual consistency. So that is the issue, okay? The more replication you have, the more you need to make sure that they're all consistent at some earliest point possible. Good. Okay, so this two-phase commit, where the boss says to everybody, "Are you all ready to attack?" They all say, "Yes, boss." And then boss says, "Okay, go for it." Okay, done. What can fail there? It sounds like a cool idea, but what is technically possible? Like, how can two-phase commit fail?
I think the old term is master node, but we're not using this word anymore. So let's say if the main node asks all the secondary nodes for being ready, and when every node becomes ready, the main node suddenly dies, then you are screwed.
Yes, correct. Sure. Or there's another possibility that's very similar. So what if the main node actually sends the actual, the commit signal, right? Then what can happen? So in other words, the first phase succeeded. So everybody unanimously said, yes, we can commit. And then the main node then sent the commit message, the second stage operation start. Okay, everybody start. Then what can happen?
Is this like when you're backing up a database?
No, I mean in the two-phase commit step. So the point is, initially, so there's a bunch of sites, right? A bunch of sites. And then, so we don't say the word master slave anymore. I mean, that's part of like our database, terminology, but okay, so say we have these nodes, right? And then in the initial step, the query step, you query everybody and say, are you all able to commit? They're all locally made operations, but they're not committed. So they all unanimously say, yes, we can commit, yes, we can commit, yes, we can commit, yes, we can commit. So then you have this, full 100%, like unanimous voting. And then the next step is, okay, go ahead and commit, go ahead. Then what can happen?
Oh, you have to wait until the data is received from all 4 nodes. Or like the arrow from like the 4 databases has to be like completed.
I think you got up a little bit cold there. You're getting warmer. So just imagine the only thing that is left to do is the actual commit. So at that point, what can happen is the question. I almost gave the answer away. So even though you signal back saying that you could commit, when I actually ask you to commit, at that point something could go wrong. Right?
If at least some of the nodes actually fail to commit despite saying they could, then we would end up with an inconsistent cluster.
Exactly. So that's basically what I was saying, right? Where you ask everybody, are you all able to commit? And then they all say, yes, we are able. But in reality, you tell them to commit. And at that point, one of them is not able. That is possible, okay? Say the power went down, the RAM became full, they was paying something. So for some reason, one of them was not able to fulfill their promise. Then you still have a corrupt database. But that is highly unlikely, okay? That's the point. That is much more unlikely compared to you're not asking anybody and half the number of nodes are going to fail and you didn't know that. So it's like much less likely, but it is possible. Okay, so that's how the first commit can fail. Or like you said, the main node can fail. Okay, cool. Hey, good. This is wonderful. We still have 4 minutes. It means I can do some today's discussion. This is great. Cool. In here, I have so little to ask you, okay? This is just all about stuff, okay? I even showed everything to you. They're all DLLs, it's like right there, okay? And then I talked about CORBA. Again, we can skip this. So CORBA is how Unix machines exchange objects across the network. And it doesn't matter what the operating system, programming language, nothing matters. I think just simply like this, nothing. It doesn't matter at all. An object is an object is an object because it's all just based on interfaces. CORBA publishes like a standard in which all applications have to obey CORBA, meaning if you want my object from any application, my game even, I'll format my object in a very specific way. I'll basically implement this interface. Then the object can be serialized exactly according to this format, and then you can have it, and then you would do the same thing back to me. Okay, it's called object request broker. So the thing that goes back and forth, meaning the thing that is sitting at the edge of my application and your application, is called the object request broker. Okay, it's called ORB. So my application is here, and the ORB interface is what translates my native memory object into some kind of CORBA complaint object. And so you receive it, and you also have an ORB. So your ORB would take the CORBA object and translate that to whatever application, whatever object format that you want, and you can operate on it, send it back. So the translation layer is called ORB, Object Request Broker. You can Google all this, by the way. This I can tell you, in the interest of time. This is the whole idea, so Yash was asking earlier, if I make a cool service, then how does the world know about my cool service? Then my answer was, you have to publish in the directory called OD, okay? So this is the publishing process. In other words, if I make a cool service, then the first thing I have to do is advertise to the world that I have a cool service. Like, what kind of query parameters does my service need? Like, what do you have to give me? What URL, and then what the query parameters are. Then if I want to use something, I don't know who you are. I go to UDI and I do a find. It's called discovery. I'm saying I'm searching for stock price in an application app. Then UDI will tell me, use Satish API and this is what you need to do. It's called finding. Then you you want to use my service, you'll send directly a message to me, and we establish a communication, and we'll send objects back and forth. Okay, so that is the mechanism. Okay. Now this will do with web services. You know, we don't do it now. Ask this though. Statistical. So you gather statistics on how something is working, gather like a lot of data on how the server is functioning. Use it to optimize the queries. Versus there's a bunch of rules, and then I would use it to do query optimization. What does this remind you of? This is a very, very specific thing, okay? What does it remind you of?
I'm thinking about I know that in C++ there's something called profile guided optimization.
Right. You know, or in Java you have hotspot, okay, you can profile. No, that is actually not that. I mean, that's a good answer. But you're talking more about different ways in which statistics are done. But this one, though, in the world, somewhere else, in a very different, although somewhat related to data application, there's software that either does this or it does this. In fact, I'll give you a hint. Historically started with this, and now the world is enamored with this.
Classical machine learning versus deep learning.
Wow, you got half of it right. Okay, it's machine learning. Okay, this is the machine learning part. Sorry. This is the machine learning part. This is not machine learning at all. What is it? In the 1980s, we had software. I worked on one of them. It's called Cyc, okay? CYC. Expert systems, exactly. So expert systems are literally where you sit down with an expert, and the expert says to you, you see this big white spot on the x-ray? This means the person has COVID. Why do you say that? Well, the spot has 2 millimeter radius, and I've seen like thousands in my life. So you basically interview an expert and make them write some rules, and then you follow it. That's called expert system. Whereas statistics is all about machine learning data. I'll just go and ask the data what it looks like. I learn the pattern in the data, then I'm going to use it, okay? That's it. Cool. So rule-based is expert systems and ML is statistical, and that's exactly what I was getting at. Yes, I've run out of time. I got a private message. Sure, I'll stop. So these we can now basically do next time. They're very simple. Then I'll do indexing. So I'll just keep going, okay? All right, you guys, as usual, good luck with the homework. See you next week.
Thank you.
You're welcome. Karishma, Yash, everybody says, thank you, you're welcome. HM, Arthur. So I've always said, bye-bye, Christian. I'll read names till they cut me off. Vaishnavi, Akash, Surabhi, a good night to all of you guys. Harshit, welcome. Oops. Jonas, Malaki, cool. You're welcome as well. Okay. Take care, everyone.